What's up, you guys? Welcome back to the channel. In today's video, I'm going to show you how to create this complete recreation of the classic game Pac-Man. We're going to do it completely in Python using the Pygame module. Alright, so I am super excited to bring you guys this complete rebuild of Pac-Man that you can see me kind of playing behind you right here. This was a recent YouTube poll I put on the channel to see what project you guys would be most interested in, whether you'd want like a full playable guitar or a complete rebuild of classic Pac-Man. You overwhelmingly voted for Pac-Man, so thank you to everyone who participated in that poll. I absolutely love engaging with the audience, and you guys have been so great in recent weeks. And just wanted to give you a heads up about what's coming in the future. So hopefully you love this project and you dive into it. And obviously let me know if you have any questions on this one in the comments below. But in the coming weeks, I am planning on getting into a little bit of home automation and robotics concepts as well. I've got an Arduino beginner pack, and we're going to take a look at how to do some basic home automation with that. So thank you to everyone who has subscribed and liked videos and left comments on Lemaster Tech. You guys have made the channel growth and expansion possible and have really encouraged me to dive into new concepts and new projects. So I want to talk to you a little bit about what's going on in the Pac-Man you see behind you. Just as I play through it, we've got this animated player with, obviously it looks a lot like classic Pac-Man, but I actually created all the graphics you see on the screen totally from scratch. And this board is not just a static image of the background, it's actually tile-based, similar to a lot of the recent projects we've made, like the recent Pygame platformer. So it's tile-based, and we give every tile a command on how to display on the screen. And the game knows how to draw the entire board just based off of that. And then we have all these different rules where if we collide with a ghost while the power-up is active, we actually eat the ghost and it just turns into little eyes and it becomes really fast and it gets back to the ghost cage where it resets and it comes back to life. The scoring is progressive just like in classic Pac-Man. And so we really tried to get the essence where all four ghosts have unique chase patterns as well, where they're all going to kind of pursue in their own slightly different ways. And then we also have restart on victory, and we have restart on loss as well. So this game is massive. It's going to take a really long time if you want to follow along and go line by line. It's a really big project. I'm going to put everything, the assets and the code, all on a GitHub, so feel free to go grab that if you would like to start with the code, especially because the board is so many tiles typed out. It could save you a lot of time to start at my GitHub and grab the code and then just follow along with the video on the parts you get confused on. Obviously, as a YouTube channel, the more watch time I get, the better. But ultimately, I just want this to be a project you guys think is really fun and cool and can kind of take and expand upon and make your own. So I hope you find the GitHub useful. I hope you find the tutorial enjoyable. I try to keep it pretty fast paced and moving along, but it's well over 1,000 lines of code for this project. So just in advance, thank you everyone for watching the video. Thank you everyone for the constructive feedback. I hope you guys enjoy making this program with me. And as always, let me know in the comments below what you'd like to see more of on the channel, what you're looking forward to in upcoming videos. And just if you found the video enjoyable, don't forget to subscribe to the channel, leave a like on the video. It helps me out a ton. And as always, thanks for watching, guys. All right, this is a massive program, so let's dive right into it. I do apologize in advance for any of my super observant viewers that there will be probably a little bit of camera shake because I am still using the integrated webcam in my laptop for this video. I had hoped to be in a bit more of a permanent setup by now, but definitely just taking a little while to get settled in Colorado, so I apologize. Hopefully it's not too bad. I'll try to be steady-handed, but just a heads up. So anytime we build any game in Python using the Pygame module, do import Pygame right in the beginning. You may need to run pip to install the module in your game. If you're struggling with pip, I just recently put a how to solve common pip problems video on the channel. Okay, so import Pygame, and then second thing to do is just pygame.init, and then I like to always put my width and my height for the game inside of variables right in the beginning. Just because more often than you might think, you actually end up wanting to reference how the overall dimensions of your game, and it can actually just be super nice to have those stored in a variable because then if, like, say when we have all the tiles for the game, we can say, oh, there's 30 tiles, so each tile needs to be width divided by 30 wide. And then doing things like that, it becomes really easy if you update the width of your game overall because you want it on a slightly wider screen. Everything you draw and design will update with you. So that's just a little bit of a detour right in the beginning here, but it's a useful thing to do, and that's why you'll always see me put those variables in there by default. So then the next thing we're going to do is pygame.display.set_mode. And then in there in square brackets, we're actually just going to give it that width and height that we made. And this is basically setting your Pygame game up to use those static overall dimensions that you created. If you didn't want them in variables, then you could just type those same numbers in here and that would work as well. So just good to know that. And then next thing is we're going to set up a timer that's going to control the speed at which our game runs. And so we'll just say timer equals pygame.time.clock. And then we'll define an FPS. This is going to be the maximum speed at which your game could play. So even if you had a really high performance computer, it wouldn't necessarily give you any kind of advantage over that FPS limit. All right, and then we're just going to kind of here in the beginning set up font because any game this size, like Pac-Man has some text that tells you like the score, and it'll probably say like game over and restart when you complete the game. So we'll just say font equals pygame.font with a lowercase f, font with a capital F. And then I use free sans bold when I haven't picked like a specific font for the game. You could put a custom font in there. I use free sans bold.ttf because it is standard on Windows installations of Python. And then let's see. So just to get the game going, that's about all we need initially. So what we'll do, just to kind of get the game window up, is then we'll come down and we'll make a game loop. And we'll say run equals true. And then while run. And so in here is everything we want to execute every single iteration of the game. So while the game is playing, all of this stuff should happen every time. The easiest one to start with is timer.tick at FPS, so the frame rate. If you don't define the frame rate separately ahead of time, then you just need to type that number in those parentheses there instead of just timer.tick at our frame rate variable. And then we'll do screen.fill, and this is just kind of putting a solid color black in the background of the whole screen. And let's just put together how to get out of the infinite while loop here, because Python really doesn't like it if you set up a while loop and you never give the code instructions on how to get out of that while loop. So what it'll be is for event in pygame.event.get, which is essentially this built-in event handling that the Pygame module has, which gets everything happening to your computer and in your computer. So keyboard, mouse, buttons, anything that Pygame can process, it's in this event.get, which means we then have to check beyond that what the type of the event was. And so the first thing we'll say is if the event type is equal to pygame.quit, which is a really unique Pygame command. It's just tied to the red X that by default is in the top of your window. So when we boot this thing up, it'll have the standard like title bar, and then there'll be a red X in the top right. That's the pygame.quit, and we'll use that to exit out of this infinite while loop. And so then the last things we got to do here are just pygame.display.flip inside the loop still, and that's basically going to that's essentially just going to let everything that we draw onto the screen, because eventually it'll be a lot more than just filling the background, and that'll draw it onto the screen every iteration. And then here outside of the loop, because this means we've hit the quit button, we're going to do this pygame.quit. And now I may have missed some stuff. I almost certainly did, but if we try to run it now, it'll tell us what's wrong. So actually that works just fine. And you may say to yourself, why did I do 900 by 950? Because you might know the Pac-Man level 1 looks fairly square. But I actually want to put some stuff like score and number of lives remaining in the bottom of the screen. So that's why it's just a little bit non-square. But yeah, that looks pretty good. So let's get into a big chunk of this thing, which is really drawing the board onto the screen. And some people might try doing it where they'd like get a JPEG for the background. So this is a pretty low def JPEG. I apologize for the image resolution. But they might try to get an image where all these channels were black, and they would just kind of steal the image from the internet. And that's totally fine. I'm not throwing shade at that. But what I think is going to be really cool, because stuff we've done on the channel before is shown how to actually design levels and how to customize a level such that we could go in and build a level editor tool, which I've put a video on how to create a level editor on the channel as well. And you could customize and build your own Pac-Man levels just by setting it up to where we can kind of design it with tiles. So I think if we look at this very awful diagram, I apologize for this, but actually everything on that board that we just looked at here can be drawn with one of these 9 tiles. So you essentially you have empty spaces, you have little dots, big dots, vertical walls, vertical lines, horizontal lines, and then you have the 4 kind of corners. And then I put this white line in there just because that's a ghost door, essentially a pathway that the ghosts can move through that the player can't. And so with these 10 pieces, just these 10 pieces here, we can actually draw everything in the game. And so what I did, so that you don't have to, is I went through and I took a look at this level that you're looking at right here on screen. And I figured out what, if we use that 10 number system, 0 through 9, how to draw this entire board using those numbers. So everywhere you see a 4 here along the top, that's just a horizontal blue line. Everywhere you see the 3s, those are going to be your vertical blue lines. So I did level 1 for you, and that'll be available for download from the GitHub as well. So you could either pause the game here, and you could copy this down if you really want to, but it's probably way easier for you. I know you have an internet connection because you're watching this on the internet. Just go to GitHub, download at least the board.py file. I will put the full code up there, but it definitely helps me a lot more if you guys follow along with the video. No pressure if you just want the GitHub. But the board.py is going to save you a lot of time. And then this is kind of what you'll want to model future levels off of too. So like the outer 2 rings for sure, like the 3s and 4s, those are going to be pretty standard in most levels. You're going to have a way to get from the left edge to the right edge. And the outer edges are always going to be something you collide with. But so anyways, I want to explain what we're doing as we get into this drawboard function, because we're basically going to check and see if the number in the board is 0 through 9, and we're going to have to set up 10 different commands for drawing the board. So that might have seemed like a bit of a detour where we didn't write any code, but I think I would have just confused you guys if I didn't cover that ahead of time. So let's go ahead and dive into right here, just underneath screen.fill. Let's just create the drawboard function, okay? And what we'll do is we'll pass in the board, but first, because I typed that board up in a separate level, then what we have to do is say level equals, and then I'm going to import it. So up here in my import statements where we have like import Pygame, I'm also going to, let's move that back up. Come on, there we go. I'm also going to say from board, because the file that I just called it board.py. I'm going to say from board import, and then I made it a list originally because my plan was to make multiple levels, and as of the time of filming, I just made the first level because I did think it'd be a great exercise after you've built this whole game to go and practice making additional levels for yourself and see if you can adapt this big program that we built together to future levels. Or at least that's my YouTuber cop-out for why there's only one level right now. Okay, so from board, import boards, and then we'll come down and we'll say level equals boards, just like that. And so if this becomes a list where you have like board 0 is level 1 and whatever, then you'd say level equals boards and then like active level, something like this, okay? But so for now, we just have the one board. We just have this exact thing here. So all we have to do is set it equal to boards. But ordinarily, you would probably put this inside another set of brackets and then make it, you know, just list 0, item 0 in the boards list. And then you'd build level 2 out to be item 1. But for now, we're just going to say level equals boards. And then in draw board, we're going to pass in the level. And now the fun begins. This is where the fun begins. And we're going to go into draw board, and we're going to start parsing out. So draw board, and then in here, I'll say we passed in level. And strictly speaking, this program will find level if you don't pass it in. So I guess it's optional to pass it in or not, but I kind of want to. So now let's define two numbers that are going to be super important in drawing this. We're going to define essentially how wide and how tall each tile should be. And so we're going to say height minus 50 because, like I said, we want that 50 kind of pixel padding at the bottom. But what you'll actually notice if you ever bother to count up the total number of squares on Pac-Man, there's actually 32 different vertical items that you need, and there's only 30 horizontal. So what we want to do is say, okay, for total height, we actually are going to divide it by 32 to get how tall each piece should be. But then for num2, it's a little bit easier because it's just straight up how wide the board is, and then divide by 30. And I'm using this special floor division symbol, which is 2 backslashes, because floor division is always going to make it an integer. And if you're giving draw commands and telling things to be at a certain spot on the screen, they have to be integers. So you guys are learning so much Python as a side. All right, so now let's go ahead and set up our nested for loops because we need a kind of a two-tiered for loop to go through the entire level that we passed in. So we'll start by saying for I in range length of level, and that's basically giving us for every single row that's inside of that level that we passed in here. And I'm not sure why it doesn't see it, but we'll worry about that later. For I in range length of level, and then for J in range length of level at I specifically. So this is essentially a two-tiered loop. Let's just get rid of the passing in level. I think we're overcomplicating it for no reason here. So let's just make this directly looking at level and get rid of the pass. That'll work. Okay, so now, oh, it's because I didn't put in, actually. That's on me. That's on me, everybody. Oh, well. For I in range length of level, for J in range length of level I. So this first one is saying we're going to do a for loop that iterates through every single row in the level. And then this is saying we're going to go ahead and iterate through every single column inside of that specific row. So basically, this is just the easiest way to go through every single tile in our program. And now we have to start building out 0 through 10. So what you see on the screen here, and I know that it might be a little bit tedious and time consuming, but just bear with me. We're gonna do some kind of cool stuff using like the .math and pi functions to draw arcs onto the screen. So that's a little unique, and I'll try to keep it moving pretty quick. So we're actually going to do nothing for 0 because it's an empty space, and 0, with us making the background black, that already works. It's just an empty black space if we type a 0 into our board. So we're going to go ahead and get started with if level at ij is equal to 1. And if it is, then that's the little dot. So we want pygame.draw.circle, and we want to put this on the screen. We want it to be white. And then we want to give it an X and Y center coordinate. That's how you draw circles. And so we'll say J times num2. So if you remember, J is what column it is. So we're giving it an X center coordinate right now. And so we want to say whatever position we are times num2, which is 30 equal spaces across the board. Then we want to say J times num2, but because that's just going to give us the starting position, we actually have to move it 0.5 times num2 again, because this is actually how to get it over to the center. We're moving it by another half space so that it's in the middle of the spot. Okay, and so that's the X coordinate, and luckily the Y coordinate is going to look very similar. So I times num1, and then plus, and then 0.5 times num1. And then we just have to decide how big we want the little dot to be. So I'm going to give it a 4 because I think that that looks pretty good just in testing and playing around. Actually, I think I've got my parentheses off here a little. Yeah, so I need a double there, and I need to get rid of 1 after this 4. Okay, so basically what we've done here is we've given it 4 arguments. What surface to draw this circle onto, and we're putting it on the screen. What color to make it, we're making it white. And then an X and Y center position, which is just basically at the center of whatever square it is. And then how big a radius to give it. And so we'll give it a radius 4. And now I'm going to kind of copy that for 2 because 2 is the big dot. 2 is the power up. And so we'll say if it's a 2, then we'll do the exact same thing, same X and Y coordinates, making our lives easier. And we'll just put 10 on the screen. And so what's kind of cool is while we're doing this, we are able to just boot it up and we'll see just the squares so that have those numbers because we haven't told it to do anything with the others yet. So if I boot this up, it's kind of fun to look at it here. You'll see just the dots that are in Pac-Man level 1. So classic Pac-Man level 1, we've got the dots going. And so we'll do that periodically every couple numbers just so we can kind of keep seeing the rewarding stuff that we're doing. So just with these simple lines of code, we're already drawing all the dots onto the screens everywhere they need to be. Okay, so let's take a look at what to do if it's a 3. So ij equal to 3. And if you kind of see where this is going and you want to try and draw the rest of these yourselves, and then you want to either kind of compare to what I do or you just want to skip ahead because you got this part, go ahead. But otherwise, I'm going to show you how to do every single one of these, okay? So for this next one, it's pygame.draw.line, and we're going to put it on the screen again. And this time I'm going to do something different. I'm going to make the color a color variable. And so initially, because again, we're just doing level 1 right now, I'm just going to set color equal to blue. But what I'll show you is all the stuff in the, let me get that picture back up. Oh, I guess I deleted the picture. Classic Pete maneuver. But so basically everything in level 1 is blue, but the longer levels, the further down the line levels in Pac-Man will have all their lines as a different color. So what you can do is when you build out more levels, just change this color variable and your draw board function is going to work perfectly just by controlling the value of the color variable. Okay, so just a kind of cool thing that we're going to do. You could totally just put blue in here if all you wanted was all your levels to be blue. That would be fine. All right, and now what we need to do is draw a line that's going to span the middle of the screen, so kind of the same X position that we had here, but from the top of the square to the bottom of the square. So in our little tile, we want it to be in the right down the middle, but from the top to the bottom. And so what we'll do is we'll say, because the way you draw a line is you give it a starting position and an end position. So it needs an X and a Y coordinate for starting position and finishing position. Hopefully, if you're a Python programmer, you at least know that a line is defined by any 2 points along the line. If not, if you don't know, now you know. All right, so I times num1 is where we're going to start this. So we're giving it starting position here. And just like I said, this X coordinate is the middle of the tile, just like it was for the dots. The Y coordinate is actually the top of the tile. So now what we do is we give it, and I'm going to put this on a second line because I like to have big text for you guys since I know that's something I need to work on. So I'm just going to put this on a second line. You can let it run on if you want. But then the finished position is going to have the same X position. It's just going to be I times num1 plus num1. So it's basically saying from the top of the square to the bottom of the square. And that's all we've got to do, okay? So we are going to then choose a line thickness. And I found for all of these lines, 3 looks pretty good. Any bigger than that and it starts to get a little chunky and jumbled. Less than that and it actually looks a little too wiry. It doesn't look that much like classic Pac-Man. So just so you can get a tester for that, let's go ahead and boot this up and you can see our vertical lines, okay? And I actually think it's really cool. Maybe it's just me geeking out, but the way we add like one tile at a time and getting to see what that contributes to the board. But I will say it all depends on how your brain works. For some people, trying to break the board down into tiles that you can craft completely from scratch in Python is not a better option than going and grabbing like the board image background and just dropping the dots in as playable objects. I totally get it. I just want to show you how I went about it. So, all right, let's go ahead and go to 4. And if we look at 4, it's just a horizontal line. So we're going to copy this whole if line equal if level equals 3, and we're going to repurpose it for 4. So in this case, we're going to start from the kind of beginning X position, and then our Y position needs to be in the middle of the screen. So if you think back to our circles, that's just I times num1 plus 0.5 times num1. So it's basically saying, all right, the first X position is at the beginning of the board, and then the second X position will be plus num2, so a full extra num2, and then headphone down. And then the Y position does not need to change for a horizontal line. So 0.5, 2 decimals times num1. There we go. And we'll keep it 3. And if we boot this up, you'll see all we're missing is the corners. So this actually looks really cool and really close already. I think that we're doing a bang up job. Maybe that's just me because I made the program. But because we have a horizontal line right here, I'm going to go ahead and sort of do something sneaky thinking ahead, because if you look back at our tiles, you'll see the only difference between 4 and 9 is actually just that it's white. For playability, it will have a difference. So when we get to the player and the ghosts like colliding with walls and what's a valid move and what isn't, we will do something different with tile 9, but in terms of appearance and drawing the board, 9 looks exactly like 4. It's just instead of whatever color the level is, it needs to be white. So if we boot it up now, you'll see the ghost door is white, and it's a unique tile that only the ghosts can pass through. Okay, so let's go ahead and do 5, 6, 7, and 8. That's the remaining stuff we've got to do, and they're these corners which use arcs. Okay, and Python and Pygame have a pretty easy way to draw arcs, but we are going to need to use Py to do it, because we're going to kind of tell the arcs what radius they need to do. And so for that, we're just going to import one more thing. We're going to import math, and you probably don't even need to run pip to import math. Most Python installations are going to have math kind of on hand and ready. All you have to do is tell it to import. And then I'm going to make another static variable similar to width and height, because we're not going to be changing the value of this variable. And it's just going to be equal to math.py. So now every time that I want to use py to kind of give radial commands, I don't have to type in math.py. I'm just going to type in all caps pi. Don't have to do it that way. That's my way of doing it, and you're watching my tutorial, so get over it. All right, sorry, that was aggressive. All right, if level ij is equal to 5, then what we're going to do now is a new one, and it's still pygame.draw, just like before, but now we're going to use one that probably you haven't seen a whole lot, and it's arc, okay? And we're still going to put it on the screen, and it's still going to be whatever color we tell it to be, so that hasn't changed. It's still a line, but now what you have to give it is a start and end position, as well as like a start and end radial position. So for example, for 5, which if we look back at the pieces, needs to be from the middle left down to the middle bottom, we're going to go ahead and give it an X and Y start here. And so we'll say j times num2 and then minus and then num2 times 0.5, and I'm going to get into why we're doing it this way in just a sec. But then, so that whole thing in parentheses minus 2. 1 second. Let me refresh. So we've got screen, color, and then we give it, yes, okay, I apologize. I got confused there. So screen, and then color, and then we give it the rectangle that this arc is going to exist inside of. So it's a little bit confusing, but if you've defined rectangles before, which I know you have, if you've watched any of the tutorials on this channel, we're constantly drawing rectangles. We need to tell it what rectangle this circle kind of perfectly fits inside. And so for this one, it's j times num2, and then back minus, and then minus a half of a unit, so num2 times 0.5. So let's look at the pieces again and kind of talk about why this is. The square that this arc exists inside is actually can be thought of as 1/4 of a circle, right? So if 5 was essentially flipped horizontally, you'd then have two squares right next to each other that look like 5 sitting next to 6. But then if you flip them down vertically, you'd have 7 right underneath 6 just like this, and then 8 right next to 7 and under 5. So what you have to do is you have to tell it what rectangle this arc exists inside of, what rectangle this is a piece of a circle that would fit right inside of. And so just to start, we'll say j times num2 minus num2 times 0.5. And I actually found we need to fudge that a little bit, and we'll get into how and why in just a second. But so, okay, this whole thing, and then the y coordinate, so the way you define a rectangle is x starting position, top left corner, y starting position, top left corner, and then total width and total height. Those are the 4 things you need to fully define a rectangle. And so the y starting position is going to be I times num1 and then plus and then 0.5 times num1. And you're saying, whoa, Pete, we just had to move the rectangle back so that we could get the whole x circle, and now we're moving the y portion down. Yeah, think about it again, okay? So the start of this rectangle that's going to have this circle in it is going to be right at the midpoint. So if we want just a rectangle, that circle would be a perfect fit inside of the box, it's going to be a rectangle that starts at this top point and over here at what the left point of 6 would be, and then it's going to go until the right point, and then it's going to go right to the bottom. So I know my drawing's not great, and this is maybe a little confusing, but after we get the arcs drawn, I'll go ahead and recap how we do this again, and hopefully that clears it up. Maybe it won't. I feel like I'm not doing a great job explaining this. Okay, so then what's kind of nice is the arc rectangle is going to be exactly num2 by num1, so we don't have to mess with those. And now we have a fully defined rectangle, and what we give it are their starting and ending positions relative to pi, so in radians. If you had basic geometry, or even if you've just cracked a geometry for children book, you probably know that a circle is 2 pi r in terms of radians, but a full circle, 360 degrees, can be described as just 0 to 2 pi. So if you think of like the sine curve, it resets after every 2 pi. So it's like 0, pi over 2, pi, 3 pi over 2, and then 2 pi is basically a full circle. So what you have to give it here, and this did require some guess and check, so if it doesn't make sense to you right away, don't worry about it. But it needs a start and end position in terms of radians, and then it needs a line thickness as well, and we've been doing 3 for everything. But so let me go ahead and explain real quickly why this bit of circle goes from 0 to pi over 2, okay? Because on a circle, if this was a full circle, this would be 0 in terms of radians. This would be pi over 2. By the time you get to a full 180 degrees, you're at pi. Then when you get to 270 degrees, you're at 3 pi over 2. And when you come back home, you're at 2 pi. So essentially, you probably know on a sine curve, it could go on for forever, but it resets every 2 pi. That's why we're doing what we're doing. If I boot this up now, because 5 is the top right corner of things, we should see a decent arc. Nope. Invalid color name. Oh yeah, because it's not color in parentheses. I made that a variable, so it's just color like that. All right, so now you see these top right corners, and what you might be able to see if you're kind of OCD about these sorts of things is they all seem just a little bit too far to the left. I thought they were a little bit too far to the left. If you like it, you can keep it. But ultimately what I did to kind of fix that, because it was sort of messing with my pseudo fake OCD that I sometimes say I have, is I shifted it just by a little bit less, and then I just subtracted 2 pixels, just like the tiniest offset, just to try to get it to line up a little better. And then if I boot it up, I found it just meshed really nicely with the curves, and it looked like a really smooth corner. So I like that a whole lot more. And now let's go ahead and do 6, 7, and 8, because I promise after my super not clear and confusing description of how to do 5, it's actually going to make a lot more sense for you. It was cool of Pygame to go ahead and change my formatting for me when I tried to copy paste. All right, so what we need to do now is just, instead of subtracting the rectangle, we're going to do plus num2 times 0.5, and then we don't need the 2. I don't know why, but this corner, 6, so I got to change the number. 6 did not have the same funky offset, and you'd think it would be the same thing in reverse, right? But for whatever reason, this actually looked really good. And then for this one, we can keep the top just the same, the width and the height just the same. And then all we have to do here is say, well, what chunk of a circle would this represent? And hopefully that discussion we just had kind of explained to you that this one starts at pi/2 and it goes to pi, okay? So, and those values are in radians again. But now if we boot this up, you'll see we get the top left edges too. And it's just starting to really come together, starting to really look good. Obviously, the only thing missing from our board are the bottom corners. So let's go ahead and do both of those before I boot it up again, because we're getting so close. So, all right, so now if level is 7, if level is 8. And now we just have to tweak our rectangles slightly again. So for this one, it's going to be jnum and then plus another half square. And again, if any of the reasons why it's back a half square, forward a half square, just take a look at the icon that we're trying to reproduce and think about where a full circle would start. Okay, for this one, a full circle would start halfway into the tile that we're trying to draw. But for 5 and 8, a full circle is going to start halfway into the tile before we're trying to draw. So I understand how kind of confusing this can be, but you have to define a rectangle that a full circle would fit inside of. So when you just need a 1/4 circle, you have to be able to kind of think visually and graphically about these numbers. All right, so this one gets scooted forward just a half circle so it starts in the right spot. And then we don't need the -2 on 7. And then what I found for this one, so this is the first one that we need to scoot up some. Similar to 5, it just looked a little better, only kind of scooting it back up by 0.4. If you don't believe me, you can play around with it. I will not be hurt if you want to keep it 0.5 just to test. Never take my word for anything. Feel free to verify. Feel free to call me out and improve on anything that I do. And then the chunk of circle for 7 is from pi, right, 180 degrees, down to 270 degrees, so 3 pi over 2. And then we want to be 3 thick again. It's just our standard at this point. You guys know that. And then for jnum, for 8, wow, for jnum, we're going to scoot it back, and we're going to scoot it back 0.4 and do the -2 because this one behaves a lot like 5. And then we are going to, for I, we're just going to subtract that 0.4 num1, just like the previous one. And then num2 and num1, that's always standard. And then this one is going to start at 3 pi over 2, and it's just going to go to 2 pi. So we're kind of completing the circle. So in a very complicated 4-step process there, we just drew like 4 different chunks of a circle. But this way, we're telling the code how to get from these integer values that we basically said, trust me, we're going to make these various numbers turn into a full level of Pac-Man just by using kind of this key. And now what you'll see when we boot this thing up, we've got an entire game of Pac-Man. Obviously, the player's not in there. The ghosts aren't in there. We don't have scoring. We don't have sound. So there's a lot of work to do still. And it may sound like just drawing the board is like not a ton to accomplish in 30 minutes, but we've just created this incredibly versatile function that now if we design new levels in the future, our function is going to be able to handle them like that. If we want to change the color, so let's do it that way just to kind of show you how awesome this is. If we change the color of the level to red at some point, this looks sweet. It literally looks like a different level of Pac-Man. So even if you didn't want to design, let's say, like multiple levels, you could make it to where like the ghost speed increases every level and you change the colors. Like this, it just gives you such a great tool and a great option. So that's the draw board function, and hopefully everything in there makes sense. Again, if you have comments or questions at any point in this tutorial, and I know some people are gonna have some questions because it is a massive project, just drop them in the comments. I'll get back to you as soon as I can on those. I'm usually pretty responsive. Life's been a little crazy recently, so if there's a few day delay, I apologize. But what I'll be doing through most of this project, just to kind of keep it a little cleaner than what I usually do, is I'm going to collapse down functions that are completely done. So you can see in my rung counter, hopefully you can see, we're going from line 19 to 47 now, and I'm only going to pop draw board back open if we need to modify anything in there, and I don't actually think we do for the rest of this project. But if we have to do any tweaking or modifications in here, I'll just expand it back out. This project, like I said, it's over 1,000 rungs of code, and if I left everything on display every time, then every time I need to add a variable, you're going to just see 30 seconds of me scrolling. Okay, so quick explanation if you haven't seen functions collapsed down like this before. It's just something that nice IDEs, I use PyCharm, they offer you these ways to kind of simplify what you're looking at. So like you can take any group of functions. I'm going to leave the while loop expanded, but we're going to do that for kind of all of our functions, okay? So I think probably the next thing to do is to draw the player, because we've got the whole board, we've got the spot for him to go, and we just don't have the player on screen. So let's go ahead and create a new function just under draw board, because we do want the player to kind of be over top of the board. And we'll just call this function draw player. So we come down here and we'll say define draw player. And we need some, obviously, we need some player images. So I'm going to go ahead and hit pass here. And I am fairly proud of these. I made them from scratch, although obviously I knew what they needed to look like. I just kind of went onto an online drawing tool and I made these pie piece images in like 3 different stages of biting. I think Pac-Man, the original game, might only have 2 images. It's like quarter open and then closed or something like that. I did 1, 2, 3, 4 in a sequence. So like if you click through these real quick, you'll see 1, 2, 3, and then open back up a little bit. So it's basically like a 4-step munching process. But we need to get these player images that I created. And again, those will all be in the GitHub as well. I also made him orange because I don't know why, but if this ever got huge on YouTube and someone like flagged it for like copyright infringement, orange kind of proves these are like my original images that I made. So maybe it won't get taken down. I don't think that would happen, but just covering my own butt there. Okay, so let's come back up kind of into where we grab all of the variables and other things like that. And let's get the player images. And we're going to do this in just a real nice and easy little for loop. So we're going to say for I in range. And then I'm going to give it a range of 1 to 5. If you're familiar with for loops, you know that if you give it a start and end range, then what it'll do is the first number will be inclusive, so it will run I equals 1, but the end number is not inclusive. So this is going to do 1, 2, 3, and 4. If you look back at my player images folder, there's 1, 2, 3, and 4. Okay? And all we're going to do is we're going to take a player images list that I'll define right above it. I'll say player underscore images equals, and then an empty list. And I'll say for I in range 1 to 5, because that's how many total images we have is 1, 2, 3, and 4. I'm going to do player dot images, or player underscore images. There we go. Dot append. Got a little ahead of myself. And append is just the Pygame command to add to a list. So append and then Pygame dot. And now I'm going to do 2 different things in here. I'm going to load the image, but I'm also going to scale it so that it's the size we want to play with. So I'm going to do pygame.transform.scale because I know I made them a little larger than 1 square. And then pygame.image.load inside. So if this confuses you, you can actually start with a pygame.image.load and not worry about the transform yet. But essentially what we're doing is we're specifying the file to load in, and I'm going to make it an F string because I want to use the I in our for loop to load in the appropriate image. So we'll do assets / player images / and then in curly brackets I, because I cleverly just named them in numerical sequence, and then .png. And that's great. That's all you have to do for the pygame.image.load portion of it. Now, after that close parentheses to finish off the load, we're in the scale now, and you give it the size to scale it down to. So you give it an X width, and then you give it a Y height, and then just make sure you close out all the appropriate numbers of parentheses, because that can get a little confusing. But so what this is doing, pretty cool, is it is taking all of the images that we have, 1 through 4, and it's making a list of just all of the images scaled down into a little 45 by 45 square, which I thought was the perfect size for playing the game. It looks just like the original Pac-Man. If you don't like it, play around with the scaling. The world's your oyster. And let's go ahead and take a look now at how to get him drawn. I don't know. Yeah, Pac-Man's a guy, right? Yeah. Let's take a look at how to get it drawn onto the screen. And so to do that, we're going to want to kind of define a player X and Y starting position. And this is a little bit of guess and check, unless you want to specify like a tile for him to start on and then do like, you know, num2 times this tile, which you totally could. But because starting position is really only something you have to deal with once, I found guess and check was fine. And that's how I came to 450-663 for this first level. If you don't like it, play around with it. That's kind of the theme of the day. And now what we're going to do is inside of our draw player function, we're just going to come in and we're going to say if. And the thing about Pac-Man is he can face 4 different directions, right? So we're going to need to make a direction variable to check what direction we're facing. But we'll say if direction is equal to 0, then screen.blit at, and then the actual image that we want to blit onto the screen is player images at, and then we need something to track how fast Pac-Man should move. So we're going to need to make a new variable called counter. I apologize. Counter divided by 5, and then we want to, so basically we need this counter to cycle through the images, and I'm doing floor divided by 5 because what I found is at 60 frames per second or thereabouts, it looks pretty good to have them cycle through a byte like every third of a second, so like 3 times a second. So basically you do all 4 of those images in 20 clicks, which is about a third of a second. So we're going to have to come up with a direction variable and a counter variable, but then we want to put the Pac-Man guy at player X, comma, player Y for position. And we're just going to kind of steal this because we can sort of, I mean, we have to rotate him, but we're going to sort of use that exact thing for 1, 0, 1, 2, and 3, which are the 4 directions. So the directions I think we'll have him go in are 0 will be right, 1 will be left, and then 2 will be, how did I do this? Up, I'm pretty sure. And then 3 will be down. So it's basically 0, right, left, 1, up, 2, and then down 3. And so now what we'll do is we'll make all these L-ifs, and we will only draw whatever position the player's in if we're facing that direction. We have the nice red squiggly lines reminding us that we need to go and define those variables, which honestly I don't mind. It'll just make sure I remember. And so now we're going to do another transform for when we do left. It's going to be pygame.transform, and then put this whole image inside of there. And then you got to do pygame.transform.flip, just like that. And then we're going to give it 2 things. We're going to say whether or not we want to flip it in the X direction, which we do, and then whether or not we want to flip it in the Y direction, which we do not for going left, okay? Other than that, you want this counter to stay the same because you want it to keep moving in any direction that it's facing. And then for the other 2, it's another transform, but instead of flip this time, it's rotate. So pygame.transform.rotate. And then for going up, we only need to rotate 90 degrees because I believe by default it's counterclockwise. I don't know. I guess we'll find out in a second. But then for direction 3, we're going to do this pygame.transform.rotate again, and we are going to rotate it 270 degrees. Interesting thing you guys can try and let me know in the comments if it works. I don't know if you can put a negative 90 here. It should work. Technically, it's the same thing as positive 270. If you've never tried it, not going to try it now. Go ahead and let me know if you do try it, and let me know if it works. We can learn stuff together. All right, and so initially we'll say direction equals 0 and counter equals 0. And just before we get too invested in this function and setting up like player controls to turn him, let's go ahead and take a look and see if that gets a Pac-Man facing right in a good starting position. And it does. I like that a lot. Obviously, he's not moving yet. We haven't set up the counter logic, and we can't turn him in any way, so he'll always be facing right. So we want to make sure that he animates when the counter is going, and we also want to make sure that we can turn him. So let's go ahead and do those two things now. All right, so right under timer.tick.fps, because we're already doing stuff that's related to time, let's go ahead and say if counter is less than 19, right? So we said 5 kind of pings, 5 frames per image. So like every image will be on there for a total count of 5, which if you remember, it's 60 FPS roughly. So 5 is 1/12 of a second. So you're going to totally cycle through the biting motion like 3 times a minute. If you don't like how fast mine goes or how slow mine goes, just mess with the if counter less than variable, and then also counter floor divided by whatever variable. That's how you can control how fast he moves, or how fast he animates, not his speed yet. Okay, but so what we'll say is just if counter is less than 19, we're just going to add 1 to it, and then we'll say else, and then counter equals 0. And we'll use this counter as well later to do kind of a fun flicker thing that the big, if you've played a lot of Pac-Man, you know the big power-up balls, the big power-up circles on the screen, they kind of flash. We'll use this counter in that position as well. But this nice little code just here, this compact 4 lines, should control kind of a 20 timer counter. And now you see this little fella is just munching away. Which is already addicting. I could watch it all day. But okay, so let's keep moving. Let's go ahead and just get him turning with the 4 arrow keys, okay? And this is going to be a little extra dumbed down right now because this is not actually how the code for turning him is going to work. I'm just going to immediately adjust the direction based on the arrow keys so that we can verify we're drawing him in the right 4 directions. So we need a new event type. So far we only have quit. We need the event type of pygame.keyDown. All right, so this is checking anytime a button on your keyboard is depressed, and try to cheer it up if you can. Bad joke. All right, so if event.type is equal to pygame dot, and then k underscore right is how you signify the right arrow key. Then what we'll do for now is we'll just say direction equals 0. And then if event.key is equal to pygame.k underscore left, all caps, then we'll say direction is equal to 1. And then we're going to go ahead and copy these guys because it's very similar for up and down, except they'll be 2 and 3. And then this is hopefully going to work right first try. Up and down, not like me displaying the arc, drawing an arc, which could have taken all day. All right, so we're facing right. I'm going to go ahead and hit the up arrow key, and he's facing up, which is pretty awesome. I'm going to hit left. Looks great. I'm going to point down. Okay, so honestly, I think this is a terrific spot that we've gotten to already. He's obviously not moving. He's not checking for collisions with the game board, but we have this animated player on a fully drawn board, and we're totally in control of which direction he faces. So if you're familiar with Pac-Man, you know that you're actually only able to turn when you have the open channel. So like we're going to set up our controls in kind of a joystick manner where like you can hold the down button down and he won't do anything until down becomes an open channel. But if you release all of the arrow keys so you're not pressing any keys, he's not going to be looking to actively move in any way. He's just going to, so even if you click the down arrow key, but he can't actively turn, he won't. And then if you release it, he'll just keep moving whatever direction he was already going. That's pretty similar to how you would replicate joystick motion just using a keyboard. So we'll take a look at that. But first, let's just do the quick and easy thing I kind of mentioned already. And let's just take care of the flickering of those big circles, because I'm worried if we don't do it right now, we're going to get so lost in functionality that I won't come back and do it later. And it does kind of, it looks really cool. It brings us closer to classic Pac-Man, which is obviously the point of this whole thing. And so what I'm going to do is I'm just going to say if counter gets greater than 3, because 3 is plenty of time for the flicker to look good. I'm going to say flicker is equal to false. But then what I'll say is else flicker is equal to true. So basically every time we reset the counter, so 3 times a second, I'm going to have it flicker for just 3 little seconds on the board. And then I think what we want to do, this is probably the only thing we'll have to adjust in drawboard all day, is we're just going to come up into our drawboard function. And for 2, we're just going to say if and not flicker. Okay, so now we're going to look at that flicker variable, and as long as it's not an active flicker, these circles will be drawn on the screen. But if it is an active flicker, nothing's going to get drawn for 2. So check out what just that simple little addition does. Okay, oh yeah, you got to define it in the very beginning. Silly Pete. All right, so flicker will be false right in the beginning, and now let's go ahead and kick it. All right, so now you see these little dots are flickering, and it looks pretty cool. If you think they flicker too fast or whatever, go ahead and just change with those settings. Like if you think they're supposed to be invisible for longer, just increase this number. If you don't like that they flicker 3 times a second, feel free to make a second counter in this same kind of style, and you can just make it whatever time you want it to be, and you can control how fast it flickers then. For simplicity's sake, I'm going to leave it there, and that's how we're going to flicker those dots, okay? So the next big thing we need to do is take a look at how to check for the player's position and check if he's colliding with various things in different directions. And that'll be what allows us to move him and control the movement. So that'll come next. All right, so let's go ahead and make a variable that we'll call check collisions position. We'll say check position, kind of check where you are on the board and if a certain like action or turn is allowed. And so basically what we want to get out of this function is we want to see, would I be able to turn left, right, up, or down right now if I wanted to? And so we'll call that check position. And I think what would be useful, rather than passing in player X and player Y, is if we gave the this function the center point of the player, because the player is essentially a circle, right? And we're going to need to check if there's a wall a certain number of pixels away from the center. And so rather than doing confusing math where like, oh, are we at the top of the player or the bottom of the player, let's create some new variables that we'll call center X. And it's just going to be equal to player X plus, and then I'm going to make it 23, even though we scaled them to 45, 45. I practiced ahead of time. I drew these onto over top of the player to kind of look at where the dot was. So like if I was to do pygame.draw.circle, draw.circle, and just put it on the screen and have it be white and have it at center X, comma, center Y, and just make it small, just make it radius 2. If I were to do that, then what we'll see, and I'll just comment this out real quick so you can see why I did this. This gets that dot. It actually might be super small on your screen, but it gets it right on the midpoint. For whatever reason, when I scaled these 45 to 45, you'd think the middle would be 22, maybe 23 if you had to pick one. It worked out that way for X, but for Y, I needed to go to 24, so there must be like one line of black just above the character or something. So anyways, that's why 23 and 24 rather than like 22 or 23, but not a big deal. Just wanted to explain where I'm getting those numbers from. And then what we're going to do is we're just going to say check position, and into check position, we're just going to pass center X and center Y, center X and center Y. And then we are expecting to get back like valid turns, right? We want to know what turns we'd be allowed to take out of there. So we can kind of just anticipate needing something. So we'll call this turns allowed. And you could call it valid turns. You could call it whatever you want. But we're going to come back up to the top, and we are going to make this variable turns allowed. And initially, we'll just say false for everything. So it's going to be 4 turns in the same order as the directions, I think. So I believe that was right, left, up, down. So this is, can I turn right now? Can I turn left right now? Can I go up right now? Can I go down right now? Maybe you're already thinking, maybe you're not, that's cool. But you might be thinking, hey, I know I can go right or left when I boot this thing up. So why wouldn't I make right and left true? And well, the thing is, this function is going to start running immediately when you boot the game up. And the function is going to tell you right away that you can turn left and right. So that's why I'm not real worried about it. Going to go ahead and collapse these for now because I don't want to jumble this too much. But so now we are getting turns allowed back from check positions, and we're passing in the X and Y position. So let's go ahead and create define check position, and then we're passing in center X and center Y. I'm going to drop the underscores while I use them in the code just so that it's obvious which variables I'm using. And then in here, I'm going to basically say turns equals false, false, false. So actually, we probably didn't even need to initialize turns allowed, but this, because every time this program runs, it's going to be overwriting turns allowed. So it literally might not need to be in the very beginning there, but that's okay. It doesn't harm anything, and this code is not going to be 1000% optimized, as you will probably pick up on. Okay, so let's go ahead and just get right into checking the position. So let's go ahead and get those 2 numbers that we'll want back in here. So num1 is going to be the height minus 50 again, divided by 32. And then num2 is going to be just simply width floor divided by 30. We're going to want these because we're going to be checking if our player's center position is kind of clear above and below and to the sides. And if you remember 0 and 1 and 2, thinking back to the board, 0, 1, and 2 are essentially the things the player is able to walk into or go through, and then 3 through 9 are going to be no-goes for the player. Once we get to the ghosts, they will be able to go through 9. So we'll be able to kind of repurpose this functionality for the ghosts. But I'm going to put the ghosts in a class, and we're going to kind of do some separate stuff from them from the player. So there's a little bit of overlap, but I actually don't think it makes the most sense to put the player and the ghosts all in the same class. So that's probably a debate that you avid Python nerds could have with each other. I'm good with it this way. And then I'm just making this num3. It's essentially like a fudge factor. So when you're playing around with this, you're going to notice we're going to say, okay, from the center of my player up above me or below me or to the right of me or to the left of me, and then minus a certain factor, because the player itself is not actually 45 by 45 like in a square. So this is just going to be a fudge factor that we're going to use in a million places, and if you didn't put it in its own variable, it could become a nightmare to kind of change it manually every time. You'll see what that means once we get into it a little more. So this whole area is going to be check collisions based on center X and center Y of player plus or minus a fudge number. And another reason you need that fudge factor is because technically the board that starts like, okay, you're in a 3, you can't drive in here now, is actually going to be half empty black space. So we don't want to set this function up to where, like, if the edge of my player hit the edge of that empty black space, then we would not be able to keep going in that direction. We want it to look like when the player's face, like the front of the player, hits the actual wall, which is in the middle. That's when you can't turn anymore. So that's why we need a fudge factor, okay? And now let's go ahead and start actually defining whether or not we can turn in these different directions, all right? So first thing we're going to do is I'm just going to handle a little something, because the player can obviously go off screen and travel through walls, which we'll handle when we get to player movement. But first, I'm just going to say if the center of X, so where the player is, floor divided by 30 is less than 29, we're going to do all these checks, okay? And the reason I'm doing it that way is because If you think back to the board, once you're in either spot 0, so all the way to the left, or 30 all the way to the right, 29 all the way to the right, you're going through the wall or you're turning around backwards. So like you're going back the way you came or you're turning to the right. Other than that, you don't need to be able to check for direction because those are always the only directions you're able to go. So what we'll do is we'll say if, and then inside we're going to do all of our actual legit checks for normal conditions, but then we'll say otherwise, then turns 0 is going to be true and turns 1 is going to be true, because there's no way you got outside of the limits of the board and you're not able to go left and right. Those are the only ways you could have even gotten there. So that's just why we need this kind of if-else framework to build everything inside of. But then from here on, I promise it's going to get a little bit more clear, okay? Or maybe more confusing. I can't control how you think. All right? So let's start and say, okay, well, if direction is right, so if we're going to the right already, then what we want to say is if for our level, so we're going to be doing a lot of checking where we are in the board. And so if level center y, floor divided by num1, and then that's the, let me get this straight. The first item is going to be the row that we're in. Okay, and we can detect what row we're in based on our Y position on the board, right? So think of this board as an array. What row we populate is going to be a function of our center Y position. And then what column we populate is going to be a function of our center X position. So when we're looking at this level and we have to give it a row and then a column, it's going to be center Y and then center X, okay? And so what I'm going to check is if my center X minus num3, so that fudge factor. And again, if you don't believe me, you can try not having it in there and just play around with it. This is already such a long tutorial that I wanted to save you a little bit of time, but I can't stop you from being curious. Go for it. Okay, so basically what we're checking is if right behind us, okay, so we're going right, we're just basically checking, is the piece right behind me less than 3, right? So 0, 1, or 2, which is empty square, small dot, or big dot. Well, if it is, then turns 1 is equal to true. Okay, and we're just going to do this very simple and basic thing for all of them before we get into the slightly more complicated ones, which is going to be checking if we're able to turn. Okay, it's always sort of logical that if you're going in a specific direction, you can probably turn behind you. But the reason we want to check, like you're basically just going back to where you came from. But the reason we want to check is because what if you had just hit a left wall and just clicked the right button, but then tried to go back to the left? We don't want a situation where like Pac-Man jumps through a wall, or maybe you do, that'd be sweet. But so anyways, we're going to do something very similar to what we just did for 0 for right, up, and down. So basically, when you're going 2, the opposite would be 3. When you're going 3, the opposite's 2, and then same for 1 and 0. So this is saying if we're going left, and now it's the same Y position, so the row that we're in, but then instead of minus num3, it's just plus the fudge factor. So now we're basically saying if my center point plus 15 pixels, which is, it came out to a pretty good fudge, but you can play around with it. If that square is still cool, then I'm able to turn right. So I'm able to go the opposite direction. And then if I'm going up, if the Y position that is, so this instead of center Y, it's now center Y plus num3. So if you're familiar with the Pygame coordinate system, higher Y numbers are going down, lower numbers are going up. So it doesn't always make intuitive sense to some people, but 0, 0 is the top left corner of your screen. Okay? So this is saying if the Y square that is below my current position, floor divided by num1, which is how wide each Y position is, and then for center X on this guy, we don't need that fudge factor now because we're checking based on exactly underneath where we are. And so then obviously, hopefully this makes a little sense to you. You see where it's going. we're saying if I'm going down, if the square right above me, so minus that fudge factor, is less than 3, then I can go back up. So this really is just the quick, simple checker to see if you can go back the direction you came for. From 90% of the time, these 4 lines right here are going to allow you to turn backwards the way you just came from. So that's kind of the purpose of them, but not 100% of the time. So it's important to include that. Okay? So that's the first thing. Now what we're going to do is we're going to check whether or not we're able to turn up and down based on our active direction. So if direction is equal to 2 or direction is equal to 3. So we can group, fortunately, a lot of the checking whether we're able to turn or not while we're going up and down. We can group a lot of it into similar buckets based on which direction we're currently going. All right, so this is saying if we're going up or down already. And what we want to do is say if my center X is, let's do it this way. If 12 to center X, and then we're going to do something here that hopefully you've seen, I've talked about in past videos. This is the modulo operator. It's essentially the remainder operator. And what I just typed on the screen here is saying if the center X position of my Pac-Man, of my player, divided by the num2, so how wide each tile is, if the remainder is between 12 and 18, then that means I'm roughly at the midpoint of a tile. So the other way you can think about this is, okay, each tile is 30 wide in this example, right? It's pretty easy to do that math because it's 900 wide. We divided it by the 30 tiles that we have. So each tile is 30 wide. If we just said, oh yeah, you're able to turn up or down as long as the entire tile below you was 0, 1, or 2, then there's going to be a span of 30 pixels where you can turn down, but most of the time it's going to look like you are going through a piece. So really what you want to do is say you're only able to turn if you're roughly at the midpoint. And 12 to 18, like a span of 6 pixels, it might sound like a lot. It's really not. You're always going to look pretty much like you're right down the pipe. You can tighten these limits a little bit if you want during testing, but I found 12 to 18 is great for making sure the player's roughly in the middle of the board. Okay? So what that whole point is just to say this is checking whether our X position would even allow a turn up or down. And so then what we want to say is, all right, now we check our position on the board. And so again, center Y plus the fudge factor, num3, and then floor divided by num1, and then center X floor divided by num2 is less than 3. So this whole line, and I think I definitely probably messed up some formatting here. I think maybe I've got too many or not enough brackets. Oh yeah, open parentheses. Dingus. There we go. Okay, so now this is saying if the position that is directly below me is open, then I want to make turns 3, which is down. Yeah, see, I get myself confused sometimes too. Turns 3 equal to true. So you can read this whole function. I know the text and the math gets a little confusing, but this whole thing that we've just typed in so far essentially reads, if I'm going up or down already, as long as I'm roughly in the midpoint, which if you think of how we're structuring this code, you should be, like you're only able to turn up and down if you're in the center of a square, but it's never a bad idea to cover your butt, okay? Then if I'm clear to the below me, I can turn down, and then if I'm clear to the above me, which is this second line, I can turn up, okay? So what we do for left and right is very similar to that. Okay, so it is if my center Y modulo with num1 instead of 2 now is between 12 and 18. So again, I'm pretty much at the midpoint of a I'm pretty much at the midpoint of a square. Then what I want to do is check, and now we're going to get rid of the num3s around the center y's because we want to be exactly at the point that we are. We're checking if we can turn left or right at our exact height, so we don't want to mess with center y anymore. Okay, and so what we're going to do this time is if level center y. Let me just make sure because I don't want to get turned around giving you guys the tutorial. All right, so now what we're going to do is we're going to say, okay, center x minus num2. So this is basically checking behind us by a full square, which makes a little bit more sense because when we're going up or down, that means that we're right in the middle of a square already. So what we want to do is we want to check a full square to the left and right. And I might not have explained this super great in the beginning, but this is actually why we're separating it out to whether we're going up or down or whether we're going left or right. Because when we're going up or down, we know that one full num2 iteration forwards and backwards will always catch whatever the next tile is. So let's just go through this and then we'll show how it's slightly different for left and right. Okay. So let's say first, if I check and I see that the tile right behind me is clear, then that makes turns 1, which is to the left, true. And then the next one is if the tile right in front of me is clear, and then that's true. Okay. And now we're going to copy this whole thing, and we're actually pretty close to done because all we have to do is modify this so that it works for left and right now. But we're going to basically say if direction is equal to 0 or 1, how are we going to make this different? We can keep the modulo checker because we're still only ever able to turn if we're roughly in the center of a tile. But now, for turns 1 to be true, rather than center x minus num2, it's just going to be minus num3. And the reason for that is, if you remember, the fudge factor is just checking against kind of the width of Pac-Man, like Pac-Man's actual body size. Whereas so these ones are going to become center y minus and plus num1. So basically, depending on the direction that we're going, we want a very realistic collision look. So we actually want to be able to keep going right a little bit longer. So that's why num3, which is a smaller number, it's only 15, whereas num1 and num2 are pretty close to 30. Because depending on the direction we're going, we want to give them a little cushion. We actually want to let the player drift a little bit into a tile that would be a no-no zone. So like we wouldn't let you turn because you're not turning down the middle of a clear path, but we are going to let you hit that wall for a more realistic looking collision. Okay, so I really hope that makes sense. I know it's sort of a complicated concept, but if you don't believe me, you're welcome to change these. You're welcome to try all 4 directions with just num3 as a fudge factor and kind of see how that doesn't work and how that doesn't look great. You know, I hope you kind of take my word for it or don't and do some experimentation like a good engineer. And let's go ahead and actually do something with this. So we have check position. We return whether or not we're allowed to turn. But really the only way for us to know if it's working or not is to set up player movement. Okay? And to set up player movement, we've actually really got to correct how we're turning the player. So right now, we have this just very basic, if the key up, if the key up, then we just immediately change the direction. But I sort of alluded to earlier, we want this sort of joystick type feel where you have to hold down a key and whatever key you hold down last is going to be in control. So rather than just change the direction right away, we're going to change a new variable we need to make called direction command. And the thing is, direction command will be conditional where, okay, I see that you're giving me the command, but I can't actually change the direction because there's a wall in my way or because I just got eaten by a ghost. Like direction command won't be as instant in changing the direction of the player. So what we'll do now is we're going to say basically if the key up, then direction command is going to be equal to whatever the direction already was, okay? And this is going to be true for, I think, all of them. Let me think. So No, it'll be this way. It'll only be if the last direction command was for that key. Okay? This might seem like an extra step. It might seem unnecessary. But let's say you were pressing 2 keys down. And your current direction is right, okay? Just so you're actively moving to the right. But then you pushed the left key, but you were still holding the right key. And then you let go of the left key because that's a mistake. You want to keep going right. If we didn't add this and the current direction command was left, then we'd be overwriting something we didn't need to overwrite. At least that's how I see it. I think that makes sense. Basically, we're just saying, oh no, I overwrote k_left, my favorite. Okay, basically we're saying if I was trying to go this way originally, like I was holding the key down, but I no longer want to go that direction, I've thought better of it. This is just saying, okay, no problem, we'll just get rid of it and we'll write the direction command to whatever direction we're already going. So basically saying this is a safe, bumpless transfer to kind of get whatever direction you want to go. And now what we're going to do with that direction command variable is we're going to say, okay, if direction command is equal, command, and actually let's do this as a for loop because it's going to be the same code 4 times. It would not take very long to type out, but it'll be cooler this way. So for I in range 1 through 5, again, because we decide to do, it'll be 4 because we want 0, 1, 2, 3. So for I in range, if direction command is equal to I and turns allowed I. So you probably are familiar with this because you guys are all experienced seasoned Python veterans. But if you have a Boolean or a true false variable, you don't have to say and turns allowed I is equal to true or anything. You can just say and turns allowed. And if you wanted is false, you would just say and not turns allowed. Because the code knows that's a true false variable. So when it checks it, it's going to say and turns allowed, which is basically saying is true or equals 1. So just a little Python hack for you. All right. And then direction equals I. And so this is where, and actually in my earliest rough draft of Pac-Man, I did not do this. I had turns allowed going like up, down, left, right for 0, 1, 2, 3. And then the direction was like left, right, up, down or something. I used different numbering sequences. If you use them the same to where direction and direction command go in a certain order, they go in right, left, up, down. Well, then if turns allowed also goes in right, left, up, down, you can do stuff like this, where rather than type in if direction command is 0 and turns allowed 0, then direction equals 0, and then also if direction equals 1 and turns allowed 1, then direction equals 1. You can just do it in a for loop. So I did mention that this code is not super optimized. That is correct, but here's one thing we just did on the fly that's pretty rad. Okay? And direction command is not defined. We also haven't made it to where the player moves at all yet, so I don't know what I thought would happen there. But okay. So we fixed the player movement there, so it's going to be much more like joystick type functionality, which is actually really cool. I really like the way this plays once we get the player moving. We're going to go ahead and throw in that player move across the screen, just so we'll say, you know, if the player X has exceeded the maximum screen width, so if he's gone over to 900, then I'm just going to move him all the way to off the screen to the left. But we're going to leave the direction alone. So if you're going right and your X position exceeds 900, you're still going to be going right, but now you'll be at minus 47. Okay, and then let's check if they've gone off to the left. Excuse me. All right, elif player X is less than -50, and then in that case, we're going to move the player X all the way over to the right of the screen. But because -50 is kind of when, too many colons, when you get to -50, you've kind of completely disappeared off the board. So we're going to move them to 897, which is like just starting to be visible. Looks pretty good. You're welcome to play around with those as with everything in this code, okay? Alrighty, so let's make our next function. Oops, sorry, bumped the table. And so this next function that we're going to make is going to be moving the player. And this is really important, but not very difficult. Essentially, whatever direction we're able to go in, we're going to move as long as that kind of collision is allowed. So let's go ahead and define it. I'm just trying to remember where I put it. Move player should be, let's just go ahead and define it. We can mess around with it. If I put it in a stupid spot, we'll catch it as we go. So let's define move player. And what's kind of cool about the move player function is we're just going to receive the X and Y position. So player X, I'll just say play X and play Y to separate it from the outside world. So player X, player Y, and I'll just remind everyone right, left, up, down, just so everybody can kind of keep it straight as we go through these numbers. But if direction is equal to 0 and we're allowed to go to 0, so here's where keeping those numbers straight is also super useful. But this basically means our current direction means we're pointed right and I'm allowed to go right, then I'm going to move the player's X by plus equals, and we're going to have to come up with a new variable called player speed, and that's how we'll kind of control what a good amount of speed for the little Pac-Man dude feels like. Okay, so otherwise, if direction is 1 and turns allowed is 1, then we want, player X minus equal player speed. And so this is going to seem fairly similar to the thing I just said was cool to do with a for loop, but because we have to just change something different with all of them that doesn't really have a numerical assignment, it kind of doesn't make as much sense to try to do a for loop for this, even though the code is fairly similar for all 4 of them. And so then what we'll do is we'll say, okay, 3 and 3, and just want to make sure I get this right. 3 is actually down, which means we increase it, and then 2 is up, which means we decrease it. And then all we have to return from this, because the only thing we changed in here, is player X and then player Y. And so let's go ahead and create that player speed variable. I think when I messed around with this, I found 2 to feel very similar to the original game. But obviously you are more than welcome to kind of mess with player speed. It could even be something fun to kind of make that adjustable, like as you get into later levels, or you could add your own kind of power-ups or whatever. You could increase or decrease speed. We'll be doing some more fun stuff with like the ghost speed, because the ghost speed is pretty important, and like they slow down when you get the power up and they've been eaten, and then when they turn into eyeballs and they're dead, they actually like go really fast back to the ghost box. I don't know what that's called, the bullpen. Okay, so anyways, let's go down under turns allowed, and let's just say player X comma player Y is equal to, and then what did we call that? Move player, and then move player X and move player, and we need to pass in player X and player Y. Okay, if we did everything right, guys, and that's a big if, when we boot this up, the player will initially be facing right, and he'll just start going right because as we designed it, he's able to go right and left initially. And then I'm going to let him hit the wall. Hopefully the wall stops him. We may have messed this up, so let's just go ahead and boot it up. I'm going to let him hit that wall. And you can see that's actually awesome. So right now I click the right key, nothing happens. If I click the down key, he turns and he goes down until he hits that wall. If I hit up, he goes up. And then if I go left, let's try to go left. I can't go left. I did something wrong. All right, we'll figure left out. Okay, I can go left when he's completely stopped. I can go left and right. So something's wrong with my cool joystick commands that I said were going to be awesome. Let's go ahead and take a look at the player commands and see why it's slightly off. But that's pretty cool. We're pretty darn close. So I think let's take a look here. If event.key is equal to pygame.k_right 0 1 2 3, that's pretty straightforward. And then if I go in a certain direction and then I release it, key up, yeah, that's okay. And then if direction command and turns allowed, direction equals I. It seems pretty straightforward. And I think the collision detection is working okay. Let me see, just for sake of troubleshooting, if I get rid of this for loop that I spent all that time talking about how cool that would be. And I just wonder if I put it in here as 4 separate lines, if that's going to solve our problem. Because that's the only thing different than when I did this kind of testing. 0, 0, 0, 1, 1, 1. It's also possible that maybe in that kind of complicated check collisions function we messed some collision detection up. But this really should be pretty smooth. Like while I'm moving, I should be able to hold down the up key, and as soon as he's able to go up, he will. Yeah, so something's wrong, because if I start going up and then I hold down left, he doesn't turn left as soon as that's a possibility. So we want to see what's going on here. Okay, sorry for the brief hold up there, you guys. If it makes you feel any better, even people who have made 1,000 Pygame games in their life still get indenting wrong. If you see this for event in pygame.event.get loop, we actually want all this code to be outside of that for loop. So I had it one indentation level too deep, which is why when I would be like stopped, completely stopped, I'd be able to turn, because that's a Pygame event. But we want the code constantly checking to see if I'm able to turn, not just when there's a new event. So if I start clicking left now, when there's no event happening, he should still turn left as soon as it does become possible. So actually getting it outside of that indentation level is super important for kind of the joystick style movement that we need. But you can see just by fixing that indentation, all the rest of the code we wrote is actually working really well. The collision to the left, the collision to the right, the top, the bottom, being able to successfully navigate. Obviously, we're not eating anything yet, and we're not being chased by anyone yet, which is nice. But you can see we've got this really awesome little Pac-Man figure, and he can't go anywhere he's not supposed to so far. I haven't play tested it that long. But he's just sort of traveling the map, gobbling things up, can't go in the Ghost's Gate. But he can go anywhere that's kind of a valid path. And so that's really outstanding. We've got the Pac-Man character moving successfully around the board, the whole board drawn. Everything looks really cool. It's looking really vintage and just super classic. So next thing we'll do is we're going to figure out how to kind of handle scoring and eating the dots. I'm not getting into the ghosts just yet because the ghosts are pretty complicated. They all move somewhat differently from one another, and they need to kind of pursue Pac-Man in their own like tracking algorithms. Because if you're familiar with classic Pac-Man, all the ghosts actually chase you in slightly different styles. I didn't spend forever trying to replicate the exact classic algorithms of the 4. I just kind of gave each of the 4 a slightly different priority pattern in terms of their pursuit angles. So we're going to get into the ghosts, but I think first and much easier is going to be check if the player is eating, check if it's a new dot, and if it is, let's erase it from the screen. And then if it's a big dot, let's figure out what to do with that. And then let's also sort of track score based off of that. Okay? So that's going to be a really easy next thing to do. And after kind of the complications of moving the player and everything, I think we could all use an easy win. I'm probably going to regret calling that an easy win, but let's dive into it anyways. So I know we're going to do the score next, so let's go ahead and just create this score equals 0 right in the beginning so we never get some grumpy like, oh, you didn't define the score kind of error message. Not that Python could ever get grumpy at you. It's not real, I guess. But okay, let's go ahead and create a new function that I guess I called that last one check position. So let's call this one check collisions. So we're basically going to check and see if Pac-Man is colliding with pieces. And let's just send score in, and let's plan on getting score back for now. We'll probably also use this to tell us whether or not it's time for like the power up, and to track like how long the power up should continue. But for now, super easy. Let's just set up check collisions to check if we are eating something, and if we are, we'll update the board, and then we'll also update the score. Okay, so this should be a really nice little clean, function. Okay, so let's go ahead and say if player X is greater than 0 and less than 870, and we can do that in one line with this kind of neat little combo that we got here. And what we're going to do is we're going to say, okay, if level, and the reason I'm saying that is because if you're outside of those limits and you try to check your place in the board, it's going to tell you that you're checking an unreal place, because while the player is able to move off screen, we can't then check and see what square we're colliding with, because strictly speaking, you're off screen, you're not hitting the board. So if you didn't put this line in here checking the player's X position, it would throw an error saying that's kind of out of the parameters. Okay, so let's go ahead and say if level and then center Y floor divided by, and then I didn't put the numbers right in here, so I guess you could define the numbers, but this is a pretty small and quick and easy function, so I'm just gonna do it right in here. 900 floor divided by 32. That's telling you how tall each piece is, and I think previously we were calling that num1. I don't know why I'm being lazy. Let's put it right here. So typically we were calling this height minus 50 floor divided by 32. I don't know why I come this far into projects and I'm like, no, I'm gonna do it a different way. Let's do it the same way. Okay, so there's num1, and then that's going to tell us our row, what row we are in on the board, and then we'll do center X floor divided by, and we'll do num2, and even though I know it's a 30 because I'm so good at math, we are just going to say this is width floor divided by 30. And then what we're going to check and see is if that equals 1. That means where my center is. And actually, if you think about the way Pac-Man's mouth opens and closes, when the center of it becomes a 1, that's actually going to look really good. It's going to look a lot like eating. Whereas if we just said the second we enter the square, I want to simulate the eating, it's going to look a little too early. So this center X, center Y is really a great way of doing it. And what we'll do is we'll say, okay, if it's a 1, then we want the level to change. So that exact piece on the board, Control C, we want it to change to a 0. So basically that means it's eaten. It was a dot. Now I want it to be clear. And then I think you get 10 points for a small square. If it's a different number of points, if you Pac-Man nerds want to correct me, then go ahead and make it whatever the proper number of points is. Then copy that whole thing. And I did not identify that we were passing it in. So score. I'll just call it score without an E. Just again, I like having it slightly different inside of the functions. You don't, I think, strictly need to do that. But if I look at SCOR or anything for that matter that's kind of funky, like it doesn't have an underscore or anything like that, like center X, center Y down here, I know I'm dealing inside of a function. It just helps me keep these a little more straight, which with how many different things are going on in this project is not a bad thing. Okay, but so it'll get a little more complicated when we want to incorporate this 2, which is the big dot, into also turning on a power up. But since we don't want to do that just yet, let's go ahead and take a look at that. I think just these lines of code right here are all we need to kind of get the simulated eating. Yeah, so look, he's clearing the board. I mean, I always laugh at this stuff because I just think this is so cool. Like, this is the whole reason to program, is just build something from scratch. And like, you could say, oh, Pac-Man exists, it's not from scratch. And it's like, yeah, well, there was no code on this screen before we got here. And then just in a couple hours of writing programming together, we've got this really cool Pac-Man who's eating his way through the board, and he's just clearing the board. So this is going really well. I think let's go ahead and display score on the bottom of the screen just to kind of show, let's start using this bottom space. And we don't really need a whole bunch of like complicated stuff. I think the best thing to do, rather than gum up this while run loop, because this main loop is already pretty full, let's go ahead and just underneath draw player, let's add another draw, and we'll just call it draw miscellaneous. And I don't think we need to pass anything in there because we're not going to edit anything in here. We're just going to display some stuff. And so we're going to call this draw miscellaneous. Make sure you got an underscore and make sure you put DEF. And then in here, first thing I'm going to do is I'm just going to render some text. So I'm going to say score text. And if you're not familiar with Pygame's text format, you have to do this font.render with the font that you define at the beginning of the game. And you have to tell it what text you want it to display, separate from just a regular string variable. So I'm going to do an F string that's going to say score and then display the score variable. You put variables inside these curly brackets. I think we talked about that already. And then true is anti-aliasing. One of my smart viewers commented on a video because I kept saying I don't know what that does. And they said it basically smooths out the edges. Who doesn't love smooth edges on their text? So we're going to do that. And then screen.blit, which is block transfer, I'm pretty sure. And it basically just means put this on the screen. And we're going to blit it at 10,920. So that's why we have that 50 gap all the way at the bottom, so that we have this nice little score text. And the reason I put this in a function is because eventually we're also going to draw like how many bonus lives we have down there and any other information we might need to give the player during the game. We've just got this nice draw miscellaneous function to stick that in. So for now, it's just got score, and you can see down there we have 80, and as we pick up these little dots, we're getting 10 at a time. It's like scoring the quaffle in Quidditch. But if we want to catch the snitch, let's go ahead and get a big box, a big circle, and you see that we got 50. I think the scoring in Quidditch is even more lopsided than that, but that's pretty darn good right there. So we have our first elements of scoring in the game, and I think really there's no way around it, even though the ghosts kind of freak me out. You'd think like, hey Pete, didn't you build this before? Don't you know how to do this? Yeah, I do, but the ghosts are that much work. I think let's go ahead and figure out what to do about eating the power up and kind of have a timer that counts while the power up is active. And then we'll start taking a look at the ghost. So when I eat those big dots, right, it should trigger like, oh, now you have a power up. So if we come down into the check collisions, which is where we check if we eat stuff or not, then we want to do something when we eat a power up. And I think what we want to do is we want to just set this variable power up equal to true. And maybe I'll just call it power because I think I'll call it power up in the outside world. And then we'll call it power count, set that equal to 0. So just in case you're already eating something in the outside world, or you already ate a power up, but you make it to another power-up dot before the last one went away, we just want to make sure we reset it every time you eat a power-up so you get the full new power-up counter. And then actually, this is just thinking forward a little bit. We're going to need a list of what ghosts have already been eaten per power-up. Because once you eat a ghost and it runs back into the little ghost box and it gets its life back, which is funny because they're ghosts, they were dead, right? But once you eat a ghost, it is able to reset. And so when we draw the ghosts, we're going to say, okay, if it's a power-up, then you need to be this blue, like this spooky ghost image. But then if I eat you, you're just little eyeballs until you make it back into the box. But then if you make it back into the box, even with the power up, you shouldn't turn back into the spooky blue. You get to just be your regular self. So when we get to the ghost, it's going to be a little complicated, but we're going to get there. So for now, let's just return all of these things. So power count, and then eaten ghosts. And let's start taking a look at how to actually use these. And I think as a result of that, we'll just want to pass these in as well. So power count, and then eaten ghosts. And the nice thing about these variables is we only change them when we eat a new power up. So other than that, they'll be straight passed through. They'll leave the function exactly like they came in the function. So now we just got to keep these three straight. So power up, a power counter, and then an eaten ghosts lists. So let's go down to score and let's start using these. And maybe seems like I'm jumping around a little bit, but it's tough to not jump around a little bit. These programs get pretty huge. So Eaten Ghost, and we'll just change their names slightly so that they're a little bit easier to use out here. And then we are going to actually do stuff with them, but first let's go up here just so we never flag any errors, and let's define them all. So Eaten Ghost right in the beginning of the game. Obviously you haven't eaten any ghosts yet, so it makes sense to make these all false. And then the power counter, we'll have it start at 0, and then power up, you don't start powered up, so we'll make that false. And that should be all we need for those. Let's go ahead and come down to our counters where we do other time related things, and let's figure out what to do with the power up. I was reading online that the power up lasts 10 seconds, especially in level 1. Some people seem to say in later versions of the game and in like Miss Pac-Man that the power-ups would last less and less time as you got into later levels. Not that much of a lore geek on Pac-Man, so we're just going to do it this way, okay? We're going to say below our counter stuff, we don't have to mess with the previous counter. We will say if power-up is active. So if power-up is active and the power counter is less than 600, which would be 10 seconds at an FPS of 60, then all we're going to do is we're going to add 1 to the power counter. So power counter plus 1. And then what we'll say is if it's power up and power counter has gotten to greater than or equal to. You could say, well, we're going up by 1. Let's just do equals 600 and we'll catch it that exact one time. Just do greater than or equal to, and that way there's no way a weird scenario gets around you. And then we set power counter equal to 0. We'll set power up equal to false, and then we will go ahead and just set all of Eaten Ghost back to falses, because the only time Eaten Ghost is ever going to be anything other than all false is while power up is active. So it makes a lot of sense to kind of reset it as soon as power up goes away. And one more thing we'll do while we're messing with time here, since we've got timers going on, let's implement a startup counter. Like, you know how when you load the game up, or maybe you don't, but now you do. When you load the game up, you get a little bit of a countdown. Like, the game doesn't just start moving, so you load up and you have a little bit of time to see the board and make a plan and stuff. Well, we'll make a 3-second timer that we'll call startup counter, and we'll control a new variable we'll make called moving. And so basically, if we haven't finished our 3 seconds yet, moving will be false, but we'll be advancing the startup counter. Startup counter plus equals 1. And then we'll say otherwise moving is equal to true. And so we just got to take these two, and we got to we just got to initialize them. So startup counter will be equal to 0, and then moving will be false right in the beginning. Okay, and then the easiest way to control this is just where we have move player, which is right here. We just say if moving. Okay, and so this way the player's movement is only going to change if moving is true. Moving will become true as soon as we finish that 3-second start timer. And what we'll do is, like, if you get eaten by a ghost, we'll reset everyone back to their positions, and we'll set the startup counter back to 0, and we'll set moving back to false. So if you get eaten, you get that 3-second like regather kind of time in your mind again. So this should be pretty good. And then we'll make the ghosts also under this, like, if moving, so the ghosts don't get like an advantage on you. So let's go ahead and check. So we load it up. We're not moving right away. That's pretty great. And now the only thing is we haven't done anything. Dang, should have. We haven't done anything if power up is true. So how are we going to know if it's working or not? Because we don't have the ghosts on the board yet. And well, that's the beauty of the draw miscellaneous function. We're going to just go up to draw miscellaneous, and I'm going to put just a blue circle down by the score while power up is active, so we can see that the power up is like actually triggering and resetting correctly. So we'll say if power up pygame.draw.circle, and then we'll put it on the screen. And then because everything turns blue when a power up is active, I'm going to go ahead and just make it blue. And I'm going to put it down to the right of the score, but still down in that kind of section close to the bottom. And I'll give it a radius of 15 just to make sure it's big enough to see. And I really think that's good enough. Let's go ahead and do one more thing since we're in the draw miscellaneous function. Let's draw how many lives we have left, and we'll do that by kind of swiping the Pac-Man image, the Pac-Man logo, because that's how classic Pac-Man does it, is they show you how many lives you have left with the little icon of Pac-Man. So we'll say for I in range lives, and obviously there's no way to lose a life yet. We haven't put collision with the ghosts in, but we're getting kind of ahead of the curve here, which is great, and drawing how many lives we have on in this really cool stylish way. Rather than just text that says like lives 2, we're going to scale the image, so player image is 0, which is kind of the cool classic Pac-Man image. So you can take any frame that you want, but I'm going to make them 0. And let's scale it down to 30/30. So it's a little bit smaller than the actual player because it's just down in the little bottom window. Okay, and then what we'll do is we'll say 650 plus I. So it's got to be some kind of function of what life it is so that we don't draw them right on top of each other. So if we put them at 650, that's enough room that you could have, like, I think up to 4 or 5 lives to the right. So basically this is going to move us 40 pixels to the right every single life. And it should give us, because I made lives 3, it should give us 3 lives on the bottom of the screen. And now, let's see. Yeah, so I got 3 little Pac-Men. Those represent my spare lives. Now if I go grab this power up, okay, you see we've got this big blue circle down here in the bottom left, and it should go away in just a few seconds, hopefully. I mean, I think a 10-second power up is actually a good amount of time. But yeah, okay, it goes away. And if we set it up correctly, I can go and get the next power up dot, and it'll come back. Okay, and so I'm not counting down in my head, but you can time it if you want. I'm going to try to go grab this other power up, and I should get 10 more seconds. So yeah, the circle never went away, but now you see we've still got like 7, 6, 5, 4, 3, 2, 1. I definitely think I counted faster than actual seconds, but there you go. It goes away. So that tells me right there that our power-up tracker is working exactly right. It resets even if we grab a second dot while power-up was already active. And so now the rest of the functionality, obviously, really comes down to avoiding colliding with, eating the ghosts, and then basically the rest of it from there is going to be kind of a win screen and then reset commands. So really there's not that much other than the ghosts, but I will say other than the ghosts is a pretty big task. So even though it's super satisfying to cruise around without enemies and just eat all these dots, we are finally at the point where I don't think we can do much more to this game other than maybe like win conditions, but I don't even think that's that useful without the ghosts in here. So let's go ahead and bring in Pac-Man's 4 arch nemesis, whatever that word is, the ghosts. All right, so we're due to put some ghosts in this game, and I feel like I've been talking about it so much that people probably think it's going to be worse than it is. It's not that bad. It just gave me a few headaches while I was initially setting this up and testing it. But look, the first and easiest thing is similar to how we loaded in and scaled the player images. We just have to do that once for each ghost. And now if you're familiar with classic traditional Pac-Man, then you probably know this already. But the 4 ghosts are blue, orange, pink, and red. And their names are, the blue one is Inky, and the pink one is Pinky. The red one is Blinky, and the orange one, this makes sense, is Clyde. Okay? And so I made all of these images as well as one for once you've eaten a power-up, what the ghosts look like. I made them this little like spooked ghost. And then once you've eaten the ghost, they just turn into eyes, and I called that one dead. And so it's just this set of eyes that floats back to the ghost box. So I made all of these from scratch again so that there was no like infringing on copyright stuff, although I do understand that like the entire I understand the entire game is technically like copyrighted because it exists, but we're not going to worry about that. So basically just the exact same way that we did all the player images, only now instead of like we're just going to do them one at a time. So Blinky is the red one. And then we're just going to copy this a few times and we're going to get all the images for the ghosts. So there's Blinky, Pinky, Inky, Clyde, and then we'll call, once there's been a power up, so they're not dead, well, they're ghosts, so they're always dead, but we'll call the power up, like blue ghost, we'll call him spooked. And then once they've been eaten, we'll just call that dead image. And so we've got Pinky, instead of red, it needs to be pink. And then Inky needs to be blue. And then Clyde just needs to be, I think I called it orange. And then spooked needs to be equal to power up, just like that. And then dead is, I called it dead. Great. And the reason we're scaling them all 45 to 45 is I used the same square. I think the raw image is, 500 by 500. So I use that same square of 500 by 500 to make all the player images and all the ghost images, so that my collision, the way we check to see if you're able to turn, will be able to more or less be repurposed into the ghost. So like the player's ability to check whether or not he's allowed to turn or not, is going to have a lot of overlap with how the ghosts work as well. So similar to how we gave the player X, player Y, and a basic direction in the beginning, we're going to do that for all the ghosts real quick too. So again, this was a little bit of guess and check and just figuring out how to get them in good starting positions. And then after they're in good starting positions, if you write your algorithms correctly for how they need to move, you don't have to worry about anything else beyond that. So you just got to make sure they're like in the middle of a tile roughly so that they can start moving. And then we just have to give them each a starting X, Y, and direction value. Okay, so this 3, like X, Y, and direction, we're going to copy that and use it again for Inky, Pinky, and Clyde. All right, so let's see. We've got Blinky, and then we're going to do Inky, and we're going to give them all slightly different starting conditions. So then I don't get to reuse the Inky part. I got to type Clyde out. Real pain in the butt. No worries. All right, so let's actually change these values because Blinky, I was reading some Pac-Man lore. I'm not going to lie to you guys. I am sick of Pac-Man after this project, so hopefully you guys are going to have a blast playing it. I'm probably never going to want to look at Pac-Man again, but I'm sure I'll get over it pretty quick. But so reading up on it, that was a long way of saying basically Blinky is the only one who starts outside of the box. Everyone else starts inside the box and has to kind of find their way out through the door in the top. So we're just gonna drop Pinky and Clyde in the same spot, Blinky a little off, a little below them, and then give them all a direction of going up. So they just kind of head out the gate initially. And then, Blinky is kind of in the top left corner. And so that's kind of all the initial stuff. And now what we want to do, because we've already kind of alluded to, we're going to track if they're all eaten or not, whether they've been chewed up or not. And so we're going to give them a few more variables that we just know we're going to need. So we're going to want a list of their targets. So basically, like, what tile are they searching for? And like I said, they do all kind of operate differently in real Pac-Man, which I guess this is becoming real Pac-Man. But we are going to give them all the same initial target, but I'll talk about how this is going to make it to where if you eat one ghost, then the ghost becomes dead and its target is going to become get me back in the box. If the power-up has been eaten, then the ghost targets are going to be to scatter, to get away from the player. But then if there's no power-up and the ghosts aren't dead, then the target needs to be the player itself because they're trying to hunt you down. Okay, so initially we'll make all of their targets the player, just kind of as default values, but we're going to create a function that's like get targets that'll actually change those values. And then we need a variable just initially for each of them that's going to track whether they're dead and whether they're in the box or not. So Blinky dead equals false. Inky dead equals false. And then because the ghosts have so much overlap other than the actual method in which they pursue, we're going to create a class for the ghosts. And then these 4, Blinky, Inky, Pinky, and Clyde, are actually just all going to be different instances of the class. And then we'll give them each a unique movement pattern. So hopefully that makes sense. Just wanted to talk through it a little bit ahead as I do this kind of repetitious setting up of variables, but basically these are tracking whether or not they're in the box and then whether or not they are dead, and we're going to use that for some of our kind of complex checks to see what image should be getting drawn and how the movement of the ghosts should be. So let's choose a speed for the ghosts as well. Let's just make it 2, which is the same speed as the player initially, because we don't want it to be too easy, but it also shouldn't be too hard. All right. And now let's start defining the ghost class. So this is quite a bit of code, but actually it's really nice because we're just going to set up this class for ghost, and we have to do this once in the beginning. But then the same code that we write here will work for all 4 ghosts as long as we set it up correctly. Okay. So class ghost with a capital first letter. That's the standard Python naming convention for classes. And then def underscore underscore init underscore underscore. And then the automatic parameter self is going to get passed in. But let's start talking about all the things that all of our ghosts will have in common. Okay, so they're all going to have an X coordinate. They're all going to have a Y coordinate. They'll all have a target, like where they're seeking. They'll all have a speed. They're all going to have an image, which actually represents what to draw on there. They're all going to have a direction. They're all going to have a variable telling us whether or not they're dead. They're all going to have a variable telling us whether or not they're in the box. And then we're going to give them each an ID, 1 through 4 or 0 through 3, to kind of say which ghost you are. So if we need to use anything out of the list, like if the ghost's already been eaten or not, we can say like, oh, okay, well, Blinky is ID 0, so set ghosts eaten 0 to true when he gets eaten. So that's kind of an easy way to do that. Okay. So let's just go ahead, and something you have to do in these initializes, if you want to use the variables you pass in this init in other functions, which we're going to want to in our check collisions, in our move, in our draw, we're going to want to use those variables elsewhere. So we just have to do this self dot and then whatever, choose an internal like variable name for it and set it equal to the raw variable name that we pass in. So we're going to do this for every variable here. So X position, Y position, and then we're going to do something very similar to what, rather than pass these in, we're just going to define them in here. But basically this is like what we did in the outside world. But I found for the ghosts, it actually works pretty good with 22. So they must just be slightly like 1 pixel further to the right or something, because the player did not look great. With 22, I needed 23 and 24, but the ghost 22 seemed to do the trick really well. Okay, so we're going to define those center X, center Y, and then self.target is equal to, not self.target, just target, and I am having a hard time spelling, probably because we are over 2 hours into this tutorial. But okay, then self.speed, just set equal to speed, and you'll probably see why we do this once we get into the sub-functions inside this class, because right now, if you haven't done a lot with classes, it might not make a ton of sense. Whoops, forgot to say what these two equal. Equals box, and then equals image, and then ID, self.id equals ID. And then, so now what we're going to do is we're going to get a few variables that we know we need because the player has them. And we're going to get them by checking our position on the board. So we're going to say self.turns and self.inBox are actually going to come from self.check collisions. So basically, because we called box right here, defined it here, and then immediately overwrite it here, we didn't have to pass it in, but we're a little too deep now. We're just going to keep going. And then self.rect is going to be an outline of like the ghost's collision box. We need this because we need to know when the player collides with a ghost. So to do that, we'll use like player circle. We'll define a circle that's the outline of Pac-Man, and we'll return a rectangle that is going to be the hitbox of each ghost. And we'll do player.collideRect with each ghost to check if if we get to eat them or if they get to take our life based on a whole bunch of variables. But so we'll return the ghost's rectangle using the draw function that we'll put in here. So I guess this is a good time to, because that's really all you do in the init, is you just kind of initialize and you say, okay, these are things I'm gonna have. And so we're gonna check collisions and draw every single frame for the ghost. So instead of putting these as like outside functions, we'll just do them right in here. All right, so that's kind of it for the init function. And so as a sub function, as a function inside this class, let's go ahead and just draw. And all we have to pass into this guy is self. Okay, because we can use self dot whatever variables for everything else in here. And we just have to return a rectangle. So we'll call that ghost rectangle so we don't forget while we're typing. But now we get to kind of do the easy thing, which is like blit the ghost onto the screen, because it's not actually a whole bunch of complicated shapes like drawing the board. It's just going to be like basically blit the image onto the screen. It's just going to be whatever image based on what conditions are happening in the game. So bear with me. I'm going to talk through all the different scenarios of why the ghosts would change shape. But the first is basically I'm going to fill in the if after I talk about what shape it's going to be. So I'll just say if true, just like that, so I can type in the condition. So the first one is going to be sometimes the ghost is just going to be whatever image we send, right? So whatever Blinky, Inky, Pinky, or Clyde image, and then it's just going to be at self.x pause self.y pause. So this is going to be the whole command if we're in a situation where it's time to draw the normal ghost. And then we're going to have two elifs in here. So we're going to have elif, and then this really isn't going to be an elif, it's going to be an else, because these three scenarios need to cover every time. The only things a ghost can really be, right, are its base image, or it could be the spooked image, which means it's the like blue ghost, right? So a power-up's active, or it could be the dead image if it's been eaten. So these are the only three things we need to worry about. But what we need to come up with, essentially, is what are the conditions for these. So at first glance, it would be pretty simple. It's like, okay, well, if I'm not in a power-up and I'm not dead, then I want to be the regular image, which is true, but we also need to consider if it is a power-up active, but you've already been eaten and you make it back to the box. So let's start thinking through these, and if you have any questions, feel free to ask them. So if it's not a power-up and I'm not dead, so and not self.dead, right? That's an obvious one because that just means you're not currently juiced, so the Pac-Man can't eat the ghost, and the ghost isn't already dead. Then it should be the regular image. So then we'll put an or in here, which would be or you have eaten the ghost of my ID, right? So this is kind of where we were talking about it's useful to give each ghost an ID, and power up and not self.dead. So I think that this is kind of saying, okay, you have already eaten this ghost in this power up life, because remember, we reset this list as soon as the power up goes away. But as soon as the power up goes away, if you're still dead, that means you haven't made it back into the box. So what we'll do when we check the ghost's position is we will reset whether or not the ghost is dead based on when they get back inside the box. Okay? So basically, these are the two times that you would want to just draw the regular ghost on the screen. So now let's take a look at when it should be the power-up. So elif power-up and not self.dead and not eaten ghost at self.id. Right? So self.dead and self.eaten ghost already, these are pretty similar because they should go true at the same time. Like when you eat a ghost, obviously power up is going to be true, but the ghost will become dead, and then that ghost will enter eaten. So because this is written after the first one, you wouldn't have a scenario where it got to this line of code, power up was active, and the ghost wasn't dead, but this condition was true. But it's not a bad idea to be thorough here anyways. Okay, so the thing is, the only other conditions that weren't accounted for in here were basically if self.dead, but we don't even need to type that, because if we set up the rest of this loop correctly, everything's pretty spot on already. We don't have to do elif, we can just say else. It's the only other condition. All right, and now we need to define a rectangle that's going to be the ghost's like hitbox, so pygame.rect, just like this, and then self.center x, and what I'm going to do is I'm just going to use the values that I know give it a pretty fair hitbox. So like these ghosts will only hit you when you've really earned it, like you've really collided with a ghost. But if you feel like this is not a big enough hitbox, or you feel like you're turning corners and ghosts are sometimes catching you unfairly, all you need to do to adjust the hitbox of these ghosts is do self.center x and self.center y minus smaller values, because what we're basically doing is we're building a rectangle by giving it two arguments. So this is not pygame.draw.rect. This is just pygame.rect.rect, which is defining a rectangle. And to do that, you give it two sets of tuples. So you give it a xy coordinate of where to start, and then an xy coordinate of how wide and how tall to make it. And so for us, we want the center x and center y to be essentially half of the hitbox below and above, because then we're going to make the width and the height just double that offset factor. So it's building a rectangle around the square of the ghost that we're going to check to see if we collide with. I know that maybe sounds a little bit confusing, but it's pretty straightforward. It's basically just we haven't done the collision with ghosts yet, and we're not going to until we're ready to put in like life reduction and then resetting. But we're just building a little hitbox, and we're not doing pygame.draw.rect. We're just defining the rectangle so we can use it later. Okay, so that's draw. And we do need to put some other stuff in here. So like obviously with check collisions, I already gave it away. We're putting in a define check collisions function next. And it needs to, return both what turns we're allowed to take, so self.turns, and also because we're checking what position we're in, we'll also check whether or not we're in the box. So we'll return self.turns and self.inBox. But basically, before we get into this one too much, I am just going to actually create the instances of the ghosts, because I think that would be useful at this point. Before we do too much extra ghost code, let's just kind of create the instances of them, because at a minimum, we get to start seeing them on the screen, which is kind of encouraging. And we can go grab a power up, and then we should see them all change to like the spooked image, which will kind of help us. It'll kind of help us see that our tracking of power ups is working. Okay. So underneath draw board and draw player, let's go ahead and define these ghosts. All right. So let's call the first one Blinky. And even though we've used about 1 million variables that say Blinky in it, like Blinky dead, Blinky in box, we haven't actually just defined Blinky, which is great because I've wanted to keep the ghost's name until we get to the class, because that's really what makes the most sense. All right. So Blinky is going to be a capital G ghost, our ghost class. And now we need to start feeding it the variables. So Blinky X is the X coordinate. Blinky Y is the Y coordinate. And then for Blinky's target, it's going to be targets 0. And again, we're going to update the targets in a function, but we are just going to define them first. And then ghost speed, is going to be all we put in here for now. And I think later we're actually going to want to make it to where the ghosts can have different speeds, because like if you've been eaten, you're supposed to be really fast. If you go back to life, you're supposed to be just regular. And then while the power up is active, the ghosts are like slowed down. So for now, I'm just going to give them all 1 because it's a little easier to mess with, but we will probably end up itemizing that as well. All right, so then Blinky image, Blinky direction. It's made it a little easier on us by making all of these start with Blinky. So then Blinky dead, and then let's go down to the next line. The next variable will be Blinky underscore box, and then the last thing we need to give it is its ID, which is going to be 0 for Blinky. Okay, so let's go ahead and just copy that, and we're going to do that for Inky, Pinky, and Clyde. I do kind of love that they were like, yeah, we'll have these hilarious rhyming names, and then the fourth one will just be Clyde. Just because we're so edgy. All right, so let's start updating these. Inky X, Inky Y, targets 1, ghost speed for now. Inky image, Inky direction, Inky dead. I'm getting tired of saying Inky. Inky box, and then 1. And then, all right, let's do Pinky real quick. Pinky, Pinky, targets 2. Pinky image, Pinky direction, Pinky dead, Pinky box, and 2. And Clyde. This one's a little different. I'm going to do copy paste for Clyde's name because I can't just change one character like all the other guys. Control C, Control V. Oh, I got Clyde underscore X. I just want Clyde. There we go. Targets 3. And then Clyde image, Clyde direction, Clyde dead, Clyde box, and 3. Okay, and I think we're good. It's going to want to indent these a little more for us, I bet. Yeah, I don't know why I chose different amounts for all of them, but who cares? Okay, so I think, I could be wrong here, I hope not though. I think if I just hit play, these will be all on the screen. I don't think we have to come in and do like Blinky dot draw, because I believe we call it in the init function. So let's see if I'm full of it or if that actually works. Ghost has no attribute turns. Yeah, that's true. So I tried to just kind of fake this thing out, but we need to at least do it like this. Self.turns equals false, 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 false. It needs to at least exist. Like we were just kind of pretending it didn't exist. So let's just go ahead and show it like this. Ghost has no attribute dead. What? Didn't I pass it in? Oh. I guess I didn't move direction or dead into a variable. Very cool. That's what happens. You know, you start doing these like 1,000-line, you do these like 1,000-line tutorials and you just kind of miss stuff. But we're troubleshooting it together, which makes it twice as fun. So that should do it. Let's see. Okay, so you can't see Pinky because I start Pinky and Clyde in the same spot. And Pac-Man's the only one who can move yet. And I will say, like, programming the movement of these guys is a bit of a complicated doozy, but it's kind of just fun having them on there. So let's go grab a power up and let's see if they all change to my, like, spooked ghost. Yeah, there we go. Okay, now let's see when the power up goes away, they should go away. And, oh, I grabbed a new power up. That's so stupid for testing. I don't know why I grabbed another power up. But as soon as this goes away, and the ghosts go back to normal, we will go back to programming. Okay, there we go. All right, so we've got the ghosts on there. They're at least drawn on. They look good. They're all unique. So let's go ahead and figure out how to check for collisions, and then we'll start getting them moving here. Okay, so we'll worry about getting the targets later. I think that for now we want to really hammer home the ghost collision checking. And it's a little bit, well, I'm not going to say even a little bit. It's a lot bit more complicated than the than the player, but it is built in a similar format. So I don't think it would have made sense to make the player another class and try to like modify it. I think this makes more sense, but you're going to see a lot of similarities. So bear with me, okay? All right, so number 1 is still going to be height minus 50 and then floor divided by 32. And then number 2 is still going to be equal to width floor divided by 30. And then number 3, I'm still going to keep it at 15. The ghost has basically the same body dimensions as Pac-Man, a little different, but the fudge factor ends up being like spot on the same. So 15 works pretty good. All right, now let's go ahead and start just kind of checking through the turns. So again, self.turns is going to be equal to, I shouldn't have deleted this, false, 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 false. Okay, and now what we're going to do is we will say similarly to before, if self.center x is floor divided by 30 is less than 29. So basically, are we at a legitimate spot? And then we'll say if level. And then, so first is row, again, right? Self.center y. So we're just checking what square we're in. Floor divided by num1. And that's our row coordinate. And then self.center x minus num3, our fudge factor. And then those guys together, so we actually need parentheses around those. Self.center x minus num3, and then floor divided by num2 if all of that is something less than 3. And even though ghosts can't eat the dots, their valid pathing is the same except for 9. So then what we have to say, and this is why it's going to look like there's way more code, but we just kind of have to add special conditions for 9. So what we're basically saying is we're still checking to see, like, the end of this is still going to be self.turns1 is true, just like it was for the player. But here we have to say or self.center y num1 self.center x minus num3 floor division over 2 is equal to 9. And then we're going to do another new row for this one. And self.inbox or self.dead. So what I realized while I was programming this is the ghosts are never going to go in the ghost box while they're alive under normal circumstances. So they only go back inside the box to kind of rejuvenate themselves, and then they need to leave. So we basically are saying that the ghosts are only able to turn well, and actually I'm thinking about this. We might come back to this. We might only want them to be able to go up or down when they're going through a 9. But yeah, so basically if they have something that's a 2, 1, or 0, or it's the ghost door and it's to their left, up, down, left, right. No, what is it? See, that's why I dropped the comments everywhere. Right, left, up, down. Yeah, so this is checking to see if we're able to go left. So basically, this would be the condition to say self.turns1 is equal to true. And even though I'm going to have to talk through all of the conditions just to make sure I've got it straight, we are going to copy this because it is a lot of stuff we can piggyback off of. But so next, for checking to see if we can turn right, it's still this center y floor division by num1, and then it's just self.center x plus num3, and then plus num3 down here as well. And everything else can stay the same, so that's it for right. And we're going to have to change it. Ooh, bring those back. There we go. We're going to have to change pretty much everything for up and down, but it's in the same general format. So let's see. Although there we go. All right, so now it's not just center y anymore. It's going to be, this one will be plus num3. And then this, we get rid of the num3 now. Get rid of these parentheses. And then this guy likewise will be plus num3, close parentheses, drop that in there, get rid of these parentheses. And this will be how we check to see if we can go, what would plus num3 be? That would be down, right? So that would be turns 3. We're getting very close to the end of this tutorial, but that also results in me getting pretty tired. But I need this project to be over. I've been working on this one for so long. We gotta get there. All right, so I'm gonna copy this one because all I have to do is change a few pluses to minuses. There we go. Minus num3, and now we're checking to see if we can go up. Okay. So that's pretty nice. That's the beginning one. But now likewise, if you remember all the stuff we did with going in the X and Y direction for the player, we have to do the same thing for the ghost. But now, yeah, we have to consider the ghost door as well. So let's come down here and let's go ahead and say if self.direction is equal to 2 or self.direction is equal to 3, and if 12 self.center x modulo num2 is less than or equal to 18, right? So nothing new in here, nothing that should be confusing if you understood it before. We're just checking that the X position is moderately close to the center line of a square. And it's nice to give them a range of 6. Again, you don't just want to say like, oh, if the remainder is less than 1, or like exactly 15, where you're exactly in the middle. Because it's just, this is giving you a little bit of a window, and it's pretty much dead down the middle of the row every time anyways, if you're at 13 or if you're at 17. So it's nice to give a little bit of a range here. And then what we're going to say is if, and we got to start thinking through all of the level conditions again, okay? So let's start with level and then center y plus num3, okay? And then floor divide by 1, num1, and that's going to tell us the row, again, that it is in the level, and then self.center x, floor divided by num2, and that needs to be less than 3, and again, here we go. It's about to get an or statement that's going to look a lot like what we had upstairs, or, it needs to be indented way more, okay, or this is equal to 9 and self.in box or self.dead. Okay? And so I'm going to move that and down again. And let's see, did that get it right? Or self.no. And self.in box, self.dead. I think that's good. Okay, oh, but that does need a colon at the end. Keep your formatting. And then, okay, so if that's the case, then that's just all of the conditions for self.turns down to be equal to true. So that's checking to see if we're able to go down. All right, now let's copy that, and let's check if we can go up. And fortunately, even though it's a lot of code, it's not that complicated to change. It's a minus here, a minus there. Change that to 2, and now we're checking to see if we're able to go upwards. Okay? So next, we're going to kind of steal this whole thing and take a look at y. Not like y as in the meaning of life, y as in the axis direction. And this time we are checking to see if self.center y modulo num2 is, or num1. Yep. And that means that we're able to turn left or right because we're roughly at the middle of a square. And now, hopefully you remember from the player, we just have to get rid of all the num3s on the center y's, and we have to add the num3s. We have to add the num3s to the center x's. So let's go ahead and just get started here. Alrighty, so first, I suppose, let's go ahead and check to see when we are able to go 0, 1. Let me just check what the left. All right, yeah, this is the tutorial's coming to the end part of the night, and I am getting tired. So, all right, self.turns 1. And so if we are able to turn to the right because we are in the mid section, then that means the center X left. Sorry, if we're able to go to left, that means it's minus num3 on the X, self.center X. So we just grab both places, we see self.center X, and we subtract num3. And again, if I haven't been clear about what num3 is, it's basically so that we have realistic looking collision with walls, because num3 is essentially half of the actual width of our sprite's bodies, because the square is like, the square is 30 wide roughly, and a little bit less than 30 up and down. But we want to have the players and ghosts turn when they're about halfway through the next square, because that's when the vertical lines are. That's what looks the best. And the ghosts and players are scaled to be a little bit more than one square. So num3 is our compensation factor. All right, so that's half of it. That's what we do in the scenario where direction is 2 or direction is 3. I'm going to copy the whole thing, but we got to be really careful to make sure we get everything changed in here. So now we're changing it all for if direction is equal to 0 or 1. Okay, and let's start at the very top and just go through cautiously, okay? So let's go ahead and take a look. If center X modulo num2 is roughly in the middle, then we have center Y plus, and now instead of num3, we're going to do num1. Yeah, let me make sure I got the num right. Okay, num1 and num1 and num1 and num1. And then same deal down here. Instead of num3 for lefts and rights, it needs to be num, not 1, 2. There we go. And let's see, why do I feel like that's not correct? Because it's not correct. Up here, when we offset these in these 1 and 2s, this turning X, this going left or right while we're already going up or down, this needs to be the minus num2, 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 so that down here our X changes are num3, because now we're going left and right. That's how we get the realistic looking turns. And so up here, because we're going up and down, these all get the fudge factor. These get the full number. Down here, because we're going left and right, these do get the fudge factor. And then, yep, num1, num3. There we go. And then these guys get num3s. So X up here should all be num2s. And then the Y's should be num3s. Yep. All right. I know the numbers are getting confusing. I know this math is getting confusing, but trust me, this function that we just made here is going to handle whether all 4 of our ghosts are able to turn at any point on the entire map. And that's a really useful piece of code. It just took a really long time to write. So good job, everybody, for sticking it out, making it here. Now all we have to do is, with this if center X, we have to do the same thing we did with the player. That was just say, all right, well, you will be allowed to still go left or right if you're outside of those limits, because that is how we let the ghosts travel across the screen too. Actually, I'm not sure if the ghosts are able to teleport like through the tubes on the sides as well, but I'm going to assume that they can. All right, and now because we said that we were also going to return whether or not we were in the box, and we're already looking at some like ghost positions, we might as well just put this easy checker in here, which is if the X position is between 350 and 550, which lines up pretty well with the dimensions of the box, and the Y position is inside of 370 and 490, which again, pretty accurate with the outer dimensions of the box, then we're going to set this self.inBox variable equal to true, and then we'll say otherwise self.inBox is false. And so this way, we're basically constantly checking our X and Y position to see if we are in the box or if we are not. Okay? So self.check collisions, which we call in the initialization, just like we do with self.draw, is pretty good. All right. So now what we're going to do, and this is really like the most complicated and convoluted and kind of irritating and time-consuming part of the entire project is we're going to start figuring out how to make the ghosts move. So just to remind you guys where we're at, I'll boot it up. Center Y is not defined. Cool. Probably because I didn't say self.center Y somewhere. What rung does it say? 138? Yeah. You got to put self every time. Did I miss it anywhere else? I'm sure I did. Yeah, I missed it a whole bunch of places. Nice. All right, well, it'll tell me if I miss it again, but let me try to catch it everywhere here. Self.center Y, self.center Y, and self.center Y, self.center Y. Boy, I missed it a lot of places. All right, let's see if I missed it anywhere else. Yes, I did. Line 118. Why didn't you tell me that before, man? All right. Center Y, center Y. Oh, my gosh. This is bad. That's why you want to be real thorough the first time, kids, dudes and dudettes. All right, that got a lot of them, but I just feel like it was probably all the way up. Let's see. There we go. All right, so the ghosts are still not moving because we have not put ghost movement in yet. But if they could tell you what they were thinking right now, Blinky would be telling you, yeah, I can go down or up or right, but I can't go left or up. These guys would all be saying, yeah, I can go wherever I want, but I got to get out of this ghost gate. So really the only way they're going to be able to tell us that is if we figure out how to make them move. So as I kind of alluded to before, they are all going to have their own movement patterns. So at first, I'm just going to make move Clyde. And this is where you could kind of step outside of the class if you wanted to, because they all have to have their unique movement patterns anyways. But I'm just going to make move Clyde, and then I'm going to kind of give all four of them that just kind of real quick. I'm going to give them the same movement command just so we can see the four of them moving. And then we will work on making custom movement rules for all of them. Okay, so for this, it's not that bad. It's just really time consuming and we have to cover a lot of scenarios. So right, left, up, down, just to remind us the order of the numbers because we are going to use them a lot. And so Clyde is going to turn whenever advantageous for pursuit. I'm going to make the other ghosts only turn at specific times. Like some of them will only turn if they come to a straightaway. Some of them will turn left and right at any time, but they'll only turn up or down if they hit a wall. And it's just kind of how you give them unique personality. So it is going to be a lot of fun, but we got to build one of them before we can start messing with them. All right, so easiest thing we'll do is we'll just say if we're going right, okay? And let's give them a default behavior, which is if self.target. And if you remember, target is going to be a X and Y coordinate pair. So, these all need to be inside the function. There we go. If self.direction is 0, and then if my X coordinate of my target is greater than self.x position, and I'm able to keep moving right. Okay, well, if that's the case, all I'm going to do is say self.x pause plus equals self.speed. So right away, Clyde's default move is if he's going right, then keep going right. As long as you're able to. That's what the self.turns means. It basically means you're not colliding with something on your right. So if I'm going right, and if my target is further to the right than my current position, then I'm going to keep going right as long as I can. All right, now we get into the more interesting stuff, which is the elif. So we'll check first elif not self.turns 0. And so this means that you were going right, and now you've hit something on your right, right? Not self.turn 0 means there's a collision to your right. And so what we want to do in that direction is to start making some complicated decision making. All right, so first we'll say if self.target 1 is greater than self.y pause and self.turns 3. Okay, so this means my target is below me on the screen and I'm able to turn down. Then what we're going to do is we're going to set our direction equal to down. So we are going to turn down and we're going to start moving the Y position plus equals self.speed. All right. And so because Pac-Man is a very fast-paced game and the ghosts do look very fluid on the screen, they move every single click even when they turn. It's smart that when you set the self.direction, you also move it a little bit in that direction right in that scan. Okay, and then we'll say, all right, so elif self.target1 is less than self.ypause, all right, meaning the target is higher than I am, and I just collide with something on the right, and self.turns2, all right, then we will say self.direction is going to be equal to 2, and then just kind of the opposite of turning down, we're going to do self.position minus equals self-speed to start moving us in the upward direction. Okay, and now we're not done. We're not even close to done. There's a whole lot more elifs. So then we have to say, okay, what if self.x target, right? Because we've checked to see if it makes sense to turn up and down. Let's say it doesn't in either scenario. All right, well then what if it makes sense to turn left? So elif the target is behind me, so self.x pause less than, and self.turns1 is true. So that means I am allowed to go left. Well, in that case, self.direction direction is equal to 1, and self.xpause is going to be minus equal self-speed. All right, so now we've checked to see if any turns are logical to pursue our target. If they are, we'll do those first. But what if they're not? What if the target is like right to our right and above us, but we can't turn up? We can only go left or down, but the target is to our right and above us, and we can't turn right and we can't go up. We still need the ghost to move. The ghost can't just sit there and wait for you to get back to somewhere it can turn. So here's where it really is just sort of like designer preference, at least the way I did it. I just start saying, okay, well, if it doesn't make sense to turn in any of these directions to pursue my target, I'm going to just turn down if I'm able to. So basically, if turns is equal to 3, then I'm going to set self.direction equal to 3, and I am going to move downward. So self.ypause plus equal self.speed. And then I said, okay, well, if I wasn't able to turn down, then my next choice would be to turn up. And these are the kinds of things where just by shuffling the order of these around a little bit, you get pretty significantly different ghost movement patterns. And that is kind of how I came up with the 4 different ways the ghosts would move for this. So if you think you kind of get the hang of where this is going, you could, so we have to do the same thing. This is just if we're currently going right, the decisions the ghost has to make. We have to do the same thing for all 4 directions, but once we get through all 4 directions, you're more than welcome to try to build 4 different movement algorithms for the 4 different ghosts and see if it works for you. Okay, so that's elif self.turns is 2, and then the last thing we'll say is, all right, so I can't go down, I can't go up, can I go left? And you really should be able to go left if you're colliding with something on your right, because there aren't a whole lot of places where you could have been going right, hit a right wall, and you couldn't go back to the left. So this is kind of like a catching all scenarios, at least it's really meant to. And in that scenario, self.direction is going to be equal to 1, and we are going to self.xpause minus equal self.speed, just like that. And then, so remember, this was all inside of elif not self.turn. So that's best case scenario is I'm going right, my target's to my right, and I can keep going right. Great, I'm going to do that. Oh no, I've collided with something on the right. That's the other scenario. Well, how about the scenario of I'm going right, I can still go right, but the target is not over there. Well, then what we do is we say elif self.turns 0 is legit, so I am able to turn right still, but the target's not over there. We say if self.target 1, so the y coordinate, is greater than self.y pause is greater than and self.turns. And this is the last one. I'm going to type 100% of it out. From here on, we're just going to kind of modify what you're seeing because they're fairly similar. They just get tweaked. But so basically we're going to say, all right, the target is not to my right, but I'm going right and I'm able to keep going right. Well, I'm going to constantly be on the check to see if I can go up or down to improve my state. So self.direction, if the target is below me, then I'm going to set the direction to 3, and I'm going to say self.y pause plus equal self.speed. So this is how Clyde is going to turn even if he doesn't hit a wall, if it's no longer advantageous for pursuing his target. All right, and now target 1 less than y pause and self.turns 2 is legit. Then we're going to set the direction equal to 2, subtract off speed. And other than that, we're not going to just turn and go left. We're going to say, okay, well, I want to go up and down at any point if I possibly can, but otherwise I'm going to keep cruising to the right because we're going to kind of assume at some point going right made sense for him. So maybe he hit a left wall, wasn't able to find his target. So he's going to go right until he can go up or down to his benefit. There's really no reason in going back to the left because you just came from there, assuming you just came from there. Okay, so this is it for one of the 4 directions for one of the 4 ghosts. So let's go ahead and copy this. Let's slap it down here. And then actually don't slap anything anywhere ever. All right. And now let's say if self.direction equals 1. And it's going to be very similar, but we have to be very thorough about making sure it all gets modified. Okay. So start by saying if the y position is greater than the y position, and I can go down. And so here's where I'm getting rid of kind of the first check. So let me kind of reiterate. We're going to prioritize something different in each direction so you never get stuck in a back and forth loop where, like, if you gave it a set of rules that was the same in every direction, you could easily just get them rocking back and forth, and there might be a corner of the map where you could hide and glitch out all the ghosts. So they're not going to have the exact same pattern, just a very similar pattern in all directions. So actually, rather than modify this, because we are going to do basically this same X checker, but first thing we're going to do is check and see if we can go down. So we'll say if my target's Y position is greater than self.Y pause and self.turns 3, then self.direction is equal to 3. Okay, so clearest way I can describe this is saying if I'm going left, but at any point I can turn down to pursue my target, I'm going to. That's going to be like Clyde's default move. So then we get into the elifs, and that's just to shake up the movement patterns a little bit. You can play around with it. You can make it the exact same in every direction if you want. I don't recommend it. Okay? So then we have this elif self.target 0, and now instead of greater than, we want less than, because now we're saying, okay, I'm going left, and the target is to my left, so I'm going to keep going left. All right, so this row can kind of be thought of as if the direction you're going is good for pursuit, keep doing it. The only thing you do before that is go down if it benefits you. Okay? So let's get into the elifs now because it's similar but different. All right. So elif not self turns 1. So I've hit something to the left. I wanted to keep going left, but I've collided on my left now. Well, if my target's Y position is below me, then I'm going to do this. So this is a little redundant, but it doesn't really hurt to leave here because on the off chance that like you are exactly at the same Y position when they collide and then you go below them, we still want them to go downwards first if it makes sense. And then we'll keep the go upwards if it makes sense check second. And then this is where we'll flip and we'll say, okay, well, if the X position is to my right and I can go right, then I will go right. And then we can leave the 3, 2 and just make this one 0 instead of 1, and then a plus instead of a minus. And then we come down, and in this elif self turns, this is elif self turns 1, we will leave the up and down checkers the same still. And I think all we need to do other than that is just update our else to say self.xpause is going to be minus self.speed. Okay, so I don't have my stopwatch out, but that second direction went way faster than the first direction, right, guys? So if we're lucky and if we're smart, then we can kind of keep that momentum going, and the last two will be just as much of an improvement as that was. Whoop. I think I tried to close it up too fast. All right, so let's grab the whole thing. Elif self.direction, bam. And now let's do 2. All right, so get back there. What are you doing? Sometimes the automatic indenting that thinks it's so super smart is actually not that smart. Surprising, I know. All right, so let's do similarly to how when you're going left, you'll go down at any point if it makes sense to you. Let's go ahead and say if I'm going upwards, I will go left at any point if it makes sense. All right, so this is pretty easy. We're just going to say if the x position is less than, so the x target is less than self.x position, and I'm able to turn to the left. There we go. Self.turns left. Then go left. And self.xpause minus equals self.speed. Okay. And now let's get into the otherwise. If my target, my y direction target is less than where I am, and self.turns is 2, then I want to go up. Okay, that means my target is above me. So self.ypause minus equals self.speed. So essentially, I'm already going up. Keep going up because your target is above you. Otherwise, if not self.turns 2 now, we're going to go ahead and kind of switch this up and down checker to be a left and right checker. Okay, so self.target 0 is greater than xpause and self.turns 0, then I want to go self.direction 0, self.xpause plus equals speed, and then this is going to be self.target 0 less than self.xpause, so that would be the scenario where we want to go left, and then self.turns 1, self.direction 1, self.xpause minus equals self-speed. Okay, now we're going to check if it makes sense to go downward. So elif self.target 1 is greater than self.ypause and self.turns 3. In that case, self.direction is 3, self.ypause plus equals y speed. So you can kind of see how the algorithm is very similar for every direction. But writing it this way will also be able to make minor tweaks to his decision-making algorithm simply by playing with the order in which some of these happen. All right, and then for the elif, because this is direction 2, I'm really just going to kind of modify it to a minimum degree, literally just because I was feeling lazy. So rather than like change it so that something other than 3 comes first here, I'm going to leave 3 first here. And then I'm going to say elif self.turns 1, then set self.direction equal to 1, and self.xpause minus equals speed, leave 0 down there. And then what we need to come down to is just our elif self.turns 2. And now we essentially just need the x and y checkers that were right up here, the 0 and 1, checking to see if it makes sense, because we still want to go left and right if it benefits us. Where was that? elif self.turns. Yeah, these guys. And we're just going to throw this in, basically saying if the x position is to my right, so my target is to my right, go right. If the target is to the left, go left. Otherwise, we are just going to keep cruising upwards. Okay? So now it's nice. We have one that's already in terms of y direction for direction 2. So when we go ahead and throw in direction 3 down here, although the tabbing is all messed up, Oh, goodness gracious. I can't catch a break today. Okay. All right, so then we'll say elif self.direction equals 3. And now let's take a look at how we modify this for 3. Okay, so we'll go ahead and say, I don't think we need, for all of them, I don't think we need a default to override the direction we're already going. So for 3, maybe what we say is go right under any circumstances. So this last one looked a lot like that already, didn't it? Self.target less than xpos. Yeah. All right, well, let's make this one, it should be, I think, self.target, right? 0 is going right, isn't it? So did I typo this? Self.target, oh no, so the target is to the left of my current X position, and I'm able to go, yeah, this should be a left. Yeah, like that. That's silly. Confusing. Okay, you gotta be careful. Okay, now this is saying if the target is to my right and I'm able to go right, then let's set the direction equal to right, and then plus equals self.speed. So basically we're saying if we're going upwards and the opportunity to go left presents itself, let's go left. And then we're saying if we're going down and the opportunity to go right to pursue our target presents itself, let's go right. Okay, so let's go ahead and say elif self.target. Now this elif self.target, and let's say that we'll go right or left if we're going down before we continue going our same direction. So elif self.target is less than xpos and self.turns 1 is available, then we'll say self.direction is equal to 1 minus equal 1. All right, now we're to the point where we can do a nice old-fashioned elif self.target 1 is less than the ypos and self.turns. I think I'm skipping over something that I like to do. Yeah, this like keep going down if it makes sense. I think we want to put that in next. This is the danger of copy paste. You don't know what you have and haven't changed. And I guess you guys, the viewers, do because you've been following along, probably yelling at me. But let's see. So if the direction is equal to 3, then we will say if, yeah. All right, first thing we want to do is this check to see if we should keep going down. Okay, so if my Y target is greater than my Y position and I'm able to go down, which is self.turns 3, then we are going to do self.ypos plus equals self-speed and not mess with direction. Then we will do an elif and then bam, elif not self.turns 3. Okay, so if I'm not able to keep going down, then what we'll do from there is if I can go X and it benefits me, if I can go in either direction for X and it benefits me, let's do that first. So that's left and right. And then next after that is going to be checked to see if it makes sense to do kind of the opposite of this. So bam, bam. Yeah, so I'm kind of manually doing this whole not self-turns thing, but that's okay because I got a little turned around. Okay, so we'll go left, we'll go right, and then we will check to see the opposite of this. So if the target is now below me and I'm able to go down, no, target is above me and I'm able to go up. Goodness gracious, Pete, you're having a day. Self.direction gets set equal to 2, and then self.speed is negative because we want to go upwards. All right, now let's do our elif we're able to turn, let's just turn. And let's say if self.turns 2, so basically, okay, if I can go up, I'm going to go up. Self.direction equal to 2. So this kind of makes Clyde's like default if he hits something while going down. If he hits something while going down and he can't turn left or right to pursue his target, he's going to go back up. So this is something you could play with later if you wanted to, just like we've been talking about. But basically for now, we're going to say self.ypos minus equals self.speed. And let's just do the other directions now. So we're not going to do 3 because that's the direction we're actually checking for. So then let's go 2, 1, and 0. And of course, 1 is going to be x pause minus equals speed, and then 0 is going to be x pause plus equals speed. And now let's do the okay. Elif self.turns, and this goes to 3. And then this is going to be if the target, my X position and Y position targets are still viable turns, then I'm going to do that even if I can keep going. But then if I can't turn left or right to benefit me, then I'm just going to keep going down. Okay, that was a doozy of a movement protocol. But now what we can do is just a real easy add-on, which is if I go off screen, right? So similar to the player, if I go off screen left, then self.x pause equals 900. And if you're paying close attention, although after 3 hours, I don't know how you could be, you may notice that I'm using slightly different numbers for the ghost than the person, and that's because if a ghost is right behind you and follows you through a portal, they do get a little bit closer to you in normal Pac-Man. I'm not exactly sure how it works, so all I'm going to do is just move them a few pixels closer to you, like if they're hot on your tail. Okay? And then what we're going to do is return the X position, the Y position, and the direction, self.direction. Okay? So we're going to send those back from the movement command, and that's just move Clyde, but what you'll see is we can just call it for all the ghosts just to get them moving. So we'll do that, but then I think we have to do the kind of get targets protocol where we sort of talk about all the different tiles that the ghosts are targeting at different times. Because like when you're in the box, your real target is just get out of the box. And then when you're out of the box, you're targeting the player. And then when you're when the power-up's been eaten, you're trying to get away from the player. And then once you've been eaten, you're trying to get back in the box. So we do need to create a get targets function. But let's see if we can get the ghosts moving for now just by going down to where we have our if moving for the player. So if moving, then we get all this stuff back from move player. And let's just take a look at adding the ghost movements in there as well. So let me make sure I do this the right way. Yeah, so this is going to be Blinky X, Blinky Y, and Blinky direction are going to be equal to, and then I'm just going to call Blinky dot move Clyde. So that's going to look a little silly, but that's just what we're going to say until we come up with all 4 of our algorithms. So all 4 of the ghosts are going to be moving like Clyde for now, just because it's sort of the easiest one to build off of for the other ghosts. And this is just to kind of get them moving so we can see some progress and enjoy ourselves a little bit. But like I said, you'll see right away that is not enough without fixing their targeting a little bit. So this will just be satisfying to see our ghosties moving a little bit. Clyde direction, and then Clyde.move Clyde. All right, and this should do it for now. Let's go ahead and take a look. 3, 2, 1. All right, we're moving, and yeah, you can see the ghosts are kind of trying to pursue us rather than get through the ghost door there, because they're trying to pursue the player, but their turn rules don't really let them do anything logical. So yeah, you can see they all kind of just sort of fart around, freak out, because they're all targeting. You see what Blinky, what the red ghost is doing that's super interesting, is just pursuing the player's starting X and Y position, and that's why these two are trying to pursue the starting X and Y position as well, because we're not updating it in the function anywhere. They're just looking at the initial target values that we give them up here. So now what we're going to do is we're going to kind of take that and we're going to build out the get targets function. Okay, so we're going to come down into our main game loop, our main while loop, and we're just going to, underneath where we said like draw miscellaneous, we're just going to add get targets. So we'll just do it right underneath draw miscellaneous, and we'll just say get targets. And what we need to say is the targets list is going to be equal to get targets. Okay, so that should be pretty easy. And what we'll pass in, because we need to know roughly where the blinkies are, we'll pass in the Blinky X, Blinky Y, Inky X, Inky Y, Pinky X, Pinky Y, and Clyde X, comma, Clyde Y. And that should give us everything we need to do. So I'm going to go ahead and collapse this ghost class for now, even though we are not done in there. And I'm going to come under move player, and we're just going to define get targets. And we just, right off the bat, we know we're going to return a target list of all of the ghost's various targets. Okay. So now this is probably the last new really complicated thing that we're going to do. So we're going to, the ghost movement is a little complicated, and we're going to have to kind of do that and change it a little bit 3 times, but it's pretty close. So getting the targets, and we're just going to take this one step at a time, but basically first we want to check where the player's position actually is, because we want to know how to run away from the player if a power-up is active. So I'm going to make these variables that all they need to be is inside these variables. But I'm basically going to say if the player's on the left half of the screen by X coordinate, then the runaway X, so if we're trying to get away from the player while a power-up is active, the runaway is going to be all the way to the right. We want to get away to the opposite side. Otherwise, the runaway is going to be equal to 0. So this is just basically me saying, how do we get away from the player if a power-up is active? And this is going to be useful in the getting targets function. So there we go. All right, and then we have a runaway X, we have a runaway Y, and now what we're going to have is the return target. So this is where they're going to go when they need to go back to the ghost box so that they can come back to life after they've been eaten. And I'm just defining it here because we use it in so many places that if you decide you want to mess around with your return target and you want to move it up or move it left or whatever, it's way easier to just have it in a variable and you can tweak it here rather than go in the 14 times that you're going to see it here in a second and change it every time. All right, so first thing is if there's a power up, if the ghosts are not already dead, so if not blinky.dead, then what we want is we want them all to flee, but I think it's kind of more fun that they flee in different directions. So we'll say blink target is going to be equal to just runaway X, comma, runaway Y. So Blinky is going to flee in both directions, X and Y. But then otherwise, if the power-up is active and Blinky is dead, that's what this means, then Blinky's target, so the blink target, and again, I'm not saying Blinky because we're inside the function, it's just easier for me to keep it straight. But then this means the power-up is active and I am dead. Well, my target is just my return target. Like I just need to get back to the box so that I can get back to life. And we are just going to copy this for each ghost. So that would be Inky, that would be Pinky, that would be Clyde. All right. So if not Blinky dead, else, and then if not second will be Inky dead, then Ink target and Ink target. But instead of runaway X and runaway Y, I'm just going to leave this as runaway X, but the player's Y. So the Y direction of the player, but the opposite X side. So essentially it's going to be try to flee in the X direction. And then for Pinky, we will do the opposite. We will flee in the Y direction, but we will head towards the player X. So the other fun part of this is the ghosts in Pac-Man are always kind of like dopey and have their own personalities. So it doesn't have to be the absolute hardest game you possibly want to play. It's actually supposed to be kind of fun and goofy. So Just giving them these different targets is kind of like a good personality for him. And so Clyde's target during a power up, I'm just going to make it the middle of the, I'm just going to make it a middle of the board. Okay. So that's what to do if the power up is active, but then else is going to mean, so if, and then else means the power up is now not active. All right. And so now what we've got to do is fairly simple, but it's similar to this two-step process we had here. We need to check if we're in the box or not. So if we're not in the box and we're not dead, then we're going to be pursuing the player, right? But if we are dead, we need to get back in the box. And if we are in the box, all we have to do is get out of the box. So let's go ahead and say if Blinky's not dead. And now let's add a condition to that. So if Blinky's X position, so blink X, Blinky X, I think I just called it blink X up here, right? Oh, I didn't even say I was receiving anything yet. Oh, that was going to throw an error. Good catch, Pete. Thanks, Pete. All right, so we got to remind it that it's receiving all these great parameters, and then we'll say blink X, blink Y, ink X, ink Y, pink X, pink I, pink Y, and then Clyde X and Y. Okay, and now we can use that, and we can say if blink X is between 340 and 560, and blink Y is between 380, blink Y, and 500. Well, then that means we're in the box. So that means that blink underscore target is equal to 400 comma 100. The other way of writing this would be if blink in box. So maybe that's faster, but I already wrote this. Okay. If, and they both work. There's no right way, wrong way. It's just what works for you. Okay. So else blink target is going to be equal to, and now instead of runaway, it's player X and Y. So these both mean we are not dead. And so if we're in the box, we just want to get out of the box. So I pick 400, 100 because it's an easy, just direct. It's always going to get them out of the box targeting that. And then otherwise, you're outside of the box now. Go get the player. And then if you are dead, the target is still the return target, just like it was up above. Okay, so now let's go ahead and just copy that for Inky. If not, Inky dead, ink, 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 ink. And maybe it would make sense to find a way to work this into the class if you want to. I am sure you guys are bright enough to do that. For me, this is not a particularly complicated copy paste, and it's honestly, it wouldn't be that big of a time saver for me. So if I was going to spend a preposterous amount of time doing my best to optimize this code, I would definitely find a way to not have this whole thing copied 4 times. But as it stands, you're going to get what you get, and you're going to like it. Okay? So if not Clyde dead, then what we'll do is we'll say, now Clyde, and then Clyde target, and then Clyde target, and then Clyde target is return target. And I think that does it, although I do think that this is just like that, right? Is that how I did it up here? Yeah. Okay. So Clyde just like that. And now all we have to do is return the list. So rather than target list, which is what I called it originally on Inception, we are actually just going to, rather than call it target list, that doesn't really do us any good. We're just going to define the list right here. So blink target, comma, ink target, comma, pink target, comma, Clyde target. Just like that. And now we are getting the entire list of ghost targets based on all of the movement, and we are getting it every scan of the code. So yeah, obviously this is pretty beefy. It's 580 lines, and we haven't made the other 3 movements, which I believe if we pop up the ghost class, yeah, movement alone, so move Clyde, took us from 164 to 300. So just doing quick math, that's about 140 lines that we'd have to do 3 more times to modify the 3 additional ghosts. So that right there is going to give us another 420. We're going to 420, nice. We're going to be at over 1,000 with just that, and we haven't done sound effects or anything else yet. We haven't done collision, we haven't done eating the ghosts or anything like that, but check this out. So hopefully now the ghosts will get out of the cage eventually. I guess I jinxed it. All right, we're going to have to fix their movement a little bit. It looks like they're not able to get out. But as soon as I got the power up, they all started kind of running away in different ways. And I can actually kind of impact where they run away to just by where I move. But it is a little troubling. It looks like they're not able to get through the ghost gate. So let's go ahead and take a look at our code here. Maybe it's because we're not telling them that they're in the box. Because they need to be in the box to get out of the box to be able to move through it. And I'm not sure. Let's take a look if we ever... self.inbox is box, and then self.inbox is check collisions. And then if they're, no, so they should be in the box. So it should be returning self.inbox is true. And then if they're in the box, they are able to go through anything labeled 9. Okay, well, we've got the ghosts moving, and we just don't have them going through the ghost door yet. So I think that's the next thing we've got to figure out here. So let's just take a look real quick at everything that's left. Let's kind of take a list so you guys know what's coming down the pipe. So get ghosts moving through ghost door. And then we want to lose a life and reset on collision with ghost, just like that. And then we want to eat ghost and send running back to cage if power up. And then I think we need sound effects, restart, and winning messages. And that's pretty much it, guys. We're getting pretty close. So there is definitely a lot of work here too. I'd say kind of in here is going to be create 3 extra movement algorithms. I don't know if I spelled that right. Create 3 extra movement algorithms. So we've definitely got a lot of work ahead of us, but you guys should be super proud of where we're at right now. And the next thing to do is just going to be figure out how to get these ghosts moving through that door. All right, so day 2, change of clothes. The last recording went so long that it got really late here, so I had to finish it up the next day. But let's keep going with getting the ghosts moving through the ghost door. And so basically what I think we're doing is we're probably just having the ghosts think that they're out of the box a little too soon. And so they're probably seeing that they could go through the ghost door, but then we're having their Y coordinate immediately, like as soon as they leave the box, say, okay, you're good, so you can have this other target now. So to fix that, we're just going to go into the get targets function, and we're going to try raising the target here a little bit for when you actually leave the ghost door. So we had it at 380. And I think we just want to lower all of them. So I found that what'll work a lot better is if we make this 340. So before they were all 380, we just want to make it so that all their targets are 340, which is going to allow them to clear the door completely before they start to think that they're actually able to move on. And so then we'll just keep their target 400, 100 until they're all the way out of that door. And then one more thing we want to do just to kind of bypass some of the collision checking, because not collision checking for the player, collision checking for the ghost, because we want to make it easier for the ghosts to detect that it's a ghost door right above them. So what we'll do is we'll just sort of skip over the additional checks, and we'll make a really direct if level self dot center y minus num3. So essentially, we just want to say if I'm going up and the spot above me is ghost door, which is block 9, self.center x, floor divided by num2. So if that is equal to 9, then we want to be able to turn up. And this sort of is something we tried to catch in the lower conditions, but this is just a really direct way of saying if there's a door above you that's a ghost door and you're a ghost and you're in the box, then you're able to get out of the box. So this is just a great thing to add. And then let's clean this up too so that it catches going through the door to the left as well, because we don't want the ghosts to be able to go off screen to the left and then it'll give us an error. So let's just say as long as it's greater than -1, which should give us, or maybe we want greater than 0, I guess. So this should just handle on the left end so that we never get these errors telling us that we're going off screen. But that should be all we need to do. And hopefully now if I boot this up, we'll see a bunch of ghosts that can actually get out of the ghost door and then start chasing Pac-Man. Okay, and it looks like it's not working yet, so something else must be messed up. Let's see here. What else do we need to do to get these guys moving through that door? Because it's pretty cool that Blinky is chasing us, and he's in a fairly logical pattern, and they all kind of scatter when I eat a power-up, which is good. But for some reason, they're not making it through the ghost door initially. So let's try to figure out what's going on here. Well, it would definitely help to say self.turns2 equals true. Doesn't do much good if you just say self.turns2. Okay, so make sure you got that equals 2 in there. Let's go ahead and test that again. Hopefully these guys will just scooch right out of the box. There we go. Oh, it's always a relief when something starts working. Okay, so now let's eat the power up, and obviously we haven't put collision in yet, but you can see they all kind of run away from the player and in their various different directions. Let's see if the player can move left and right through the walls. He can. Now let's try to get a ghost to chase me, make sure that works. And the ghost does chase me through the wall. Okay, so that's pretty good. Eat the power up, they sort of run away. And they all sort of run away in different directions. They scatter, which is really cool. I mean, again, our ghost movement is veering a little bit off of the original Pac-Man algorithm just because it's, I believe it's all documented out there, but we're kind of building this entire thing from scratch to replicate Pac-Man. So I think this is a pretty good fill-in that we've got going on. All right, so I think we can officially check off on our kind of remaining tasks list. I think we can officially check off get ghosts moving through the door. So I think it's time to figure out how to lose a life and reset on collision with a ghost. Okay, so to do that, let's start by creating a player circle that's, we're just going to come up by draw player, and we're going to draw a circle on the screen that's going to represent the player's hitbox, because we have just an image right now. So the game isn't really intelligent enough to know that the image we're blitting on there is a circle, and we would have to either grab the mask of that image or just define a circle, which is nice because Pac-Man's a circle, and we'll use that as the hitbox. So to do this, we'll do pygame.draw.circle. We'll put it on the screen, and to start, we'll just make it like pink so that it's really easy to see. But then once we know that it's a good size, we'll draw it as black, and we'll draw it behind the player so you won't see it. But we want to make sure we get it the right size first. So it's going to be a circle that's going to be centered on center X, center Y, and we're going to make it 21 because that's about Pac-Man's radius, and we'll just make it 2, so it's pretty thin. And we're going to go ahead and just take a look at if that's a good circle. And pink is not a defined color. That's cool. We'll make it purple. Pygame only has certain colors defined. Center X is not defined. I believe it is, unless I called them out down here. Yeah. All right, I defined center X and center Y lower than that. So we'll just come up here and define them up here. And let's try that. Okay, so you can see this purple circle I think is pretty good. It's almost exactly the outer dimensions of Pac-Man. And so if you want, maybe I'll cut it down to 20 just because I think it's a little too on the outskirts. And like in Pac-Man, it really is sort of like when the Pac-Man and the ghosts have a clear collision. Yeah, 20 looks better. So we'll do that. And now instead of purple, I'm going to make this black, and then I actually don't want to see a circle over top of my player. So I'm just going to take these 3 lines and I'm just going to put them above draw player instead of below draw player, just like that. And then this should give us, yeah, so now we have an invisible circle behind the player that you can't see, that is representing the hitbox, and you'll see why this was so important, because now we're going to set up collision between the player circle and the ghost rectangles that we returned before. Okay, so next we have to come down a little bit below here, and we're going to check for collision between the player circle and the ghost rectangles. Okay, so let's come just above the event handling here, and let's take a look at the first scenario, which is we don't have a power up. So if not power up, okay? Then if player circle dot collide rect, and then all you have to put in here is the ghost rectangle. So Blinky underscore rect, and we want to make sure that Blinky's not dead, because if you collide with a dead ghost, it is not going to do this stuff. It's Blinky.rect, not underscore rect. Okay, so if we do this, then that's basically saying that we've collided with a ghost and we need to lose a life. So all we're going to do is we're going to take this exact thing and we're going to copy it for each ghost. If they had numerical names where we could kind of cycle through a for loop, this would maybe be a little easier. Or we could put them all in a list of ghosts, and then that would also make things a little easier. But it's really not the end of the world to just copy it 4 times. And like I said, I think some of the Python studs that watch these videos are going to have a blast going through and fully optimizing this code, because I understand that it is not perfectly flawless, as almost no code ever is. But this got jacked up. There we go. So we just need this to be Inky, Blinky, Pinky, or Clyde. And these are the 4 different ghosts that you could collide with, and you don't have a power up, and they are not already dead. And so, okay, if you collide with one of those 4, first thing we're going to do for now is just lives equals minus equals 1. And we're going to add a lives checker in here. So if lives is greater than 0, or actually, I guess we want it to be greater than -1, because I think you can play when you have 0 lives, right? I think in Pac-Man, say you start with 3 extra lives, you can get hit a total of 3 times. And so actually, if lives is greater than, if lives is greater than 0, then we're going to subtract 1 life. If lives is equal to 0, then we're going to have to do game over conditions, okay? So what we're going to do is we're going to take 1 away from lives. We're going to reset that startup counter. So startup counter equals 0. And then we're just going to move everybody back to kind of starting position. So we're going to go up where we have player X, Y, direction, direction command, and then all the ghost directions and direction commands. And we're going to grab all those and sort of put them back in their initial position. So let's see, we've got Clyde direction, Blinky direction, player direction. And we're just going to copy all these down into our what do I do if I collide with a ghost commands, which is right here. So under startup counter, we are going to reset player X and player Y and direction command. And then Blinky X, Blinky Y, direction, Inky, 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 Pinky, 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 Clyde, 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 Clyde. Okay, cool. And then I think we will grab all of their are they dead commands, and we'll reset those as well. So Blinky, dead, dead, dead. Yeah, and we don't have to reset whether or not they're in the box, because, but we will reset the eaten ghost list. We don't have to reset if they're in the box, because our function is going to immediately check whether or not they're in the box. So this should be okay. We'll get rid of the targets line. We don't need that. But essentially what we're doing here is we're saying, okay, you've collided with a ghost. That's going to cost you a life. And now we're going to reset a whole bunch of stuff back to starting positions. All right, so it's not that complicated, but it is important to get all that stuff right. And you'll kind of be able to tell through just trial and error if you caught anything or if you missed anything. So that's a good place to start with that. And now we get into the non-if condition. So we had if not power up. Now we want if power up and player circle dot collide rect with Blinky's rectangle. So we'll start with Blinky. He's kind of head ghost in my mind, I guess. And not Blinky dot dead. Okay? So just like that. Then what we'll say is, oh, okay, well now Blinky is dead because we had the power up active. And then we set eaten ghost equal at 0 equal to true. And so this is basically saying we've collided with the Blinky ghost, and Blinky wasn't already dead. And then Blinky will become dead, and then we will check Blinky off as an eaten ghost. And so actually we want another condition in here, which is and not eaten ghost 0, because you actually can't eat the same ghost twice in one power up. If they get back to the box and then come out and chase you again in one power up, then you can't eat them again and they'll get you. So if not power up, we'll probably have to come back and add to this. Let me try to remind myself for that later. Add to if not power up to check if eaten ghosts. All right, so we'll probably have to come back and check that out, but let's try to get the bulk of this done first. So the next thing is we'll just kind of copy this 4 times for all of the ghosts. So that's Blinky, and then Pinky, and then Inky, and that'll be Clyde. So here we go. Inky, Inky, and not eaten ghost. Inky is 1, yeah. Then 1, and then this is 2 and 3, and this will be 2 and 3, and then this is Inky dead becomes true, and then this will be Pinky, and this will be Pinky, and this will be Pinky. I'm so tired of these ghosts' names. I'm sure you guys are too. But it'll be fun once it's working. All right, so Clyde, and then Clyde, and then Clyde. And so this should handle us being able to eat all of the ghosts initially. And I think that's pretty much it for collision. So we've handled here if power up and player circle collide with Blinky and not Blinky dead and not eaten ghosts. Then I think maybe now, just before we get into this, I think we should probably update this to be if power up and collide and Blinky dead and not eaten ghost. We should probably figure out how to reset everything in here, because right now we just have an if not power up, and I think we need another one just like this that's if power up but the ghost has already been eaten. So this will be kind of repetitive but important. And so let's say if power up and player collide circle like this, if it is a power up but we collide with Blinky and eaten ghost 0, because it's really important when you set up these if kind of loops. It's really important to catch every scenario, okay? So this is pretty rare because it's going to be hard for a ghost to get all the way back to the box, reset its life, get out of the box, and come get you while one power-up is still active, but we do need to just have it right if it happens. So we're going to do this now 4 times for each ghost. All right, now I'm going to minimize it because we don't have to change that part, but we will say Inky and then 1, and we got to do this 2 more times, okay? If power up and we collide with Pinky and eaten ghost 2, or if we collide with Clyde and he's already been eaten. And we're going to add in here and not dead, because if we collide with him and he's been eaten but he's actively dead, then it's not a problem. Right, because that just means we're running into eyeballs that are trying to make their way back to the ghost hut, and we don't really care. We don't lose a life if that happens. So it's important to be thorough and think through all the weird scenarios. But let's go ahead and check and see if now we're able to eat the ghosts and if they will run back to the cage once we eat them and then turn normal and try to get out again. Okay, so let's boot it up. And first thing's good. They all get out. I'm going to kind of sit here and let them come after me. And now I get this. Oh, okay. And I collided with them while the power up was active. Okay, interesting. So just initially I can see we did not reset power up to false when we died. So let's go ahead here and make sure we add this to everything. So power up equals false and power counter equals 0. And let's add that in everywhere. And I know you guys are like, oh, well, every time you change this like reset code, you have to type it in 5 times. That should definitely be in a function. You're right. Good call. I'm just, we're like 4 hours deep. And at this point, I want to get it to where you guys have a playable game and you can kind of go through and make it your own in the long run. Okay? So let's see if that handles it. All right, so I'm going to get this power up. So power up is active now. And all right, I collided with the ghost and it wasn't eaten yet. And so that should have been if power up and collide and not Blinky dead and not eaten ghost 0. And so maybe this is just if collide and we have eaten ghost 0, but Blinky is not dead. But that's pretty weird because they should all be dead. So let's see. This would kill Blinky dead. This would be Inky dead. That would be Pinky dead. And then that would be Clyde dead. So these maybe will solve this whole thing if we just put these above there. Sometimes the order of that kind of stuff can jack it all up. So let's just see if us checking that collision afterwards was messing it up. Because I just want to eat a ghost. Is that so much to ask for? Come back here, grab this guy, and go kill a ghost. All right, I got 2 eyeballs. That's great. It does look like they're heading, so they got stuck. So we're going to have to figure out a way to fix their algorithm because they kind of returned to a weird spot and they're stuck there. So let's see, when they're dead, we're going to have to kind of fix their pursuit algorithm, even though it's cool that I'm able to get all their eyeballs stuck in there. Let's see if, because now Blinky is trying to get back to the cage, if he's able to get there. Nope, looks like he's, he's taking the long way. All right, well, Blinky gets back in the box, but we don't set him back equal to alive. So this would be a really easy version of Pac-Man to win, where the ghosts just all get stuck or go back in the box and then don't come back to life. So I think next thing we need to do is take a look at how once the dead ghost gets in the box, they're no longer dead. So let's take a look at how to do that. Okay, and so I think this is going to be a pretty easy little add. We're just going to come down to the bottom and check if Blinky is in the box and Blinky is dead. Then we're just going to say, all right, Blinky's not dead anymore, so Blinky dead equals false. And then we're just going to copy this 4 times, and we're going to make that for each ghost. Because this is just really the easiest, simplest, fastest way that doesn't always make it the most Pythonic. But that will just say, all right, if our eyeballs manage to get back to the box, then we want them to be alive again. Clyde dead. Clyde dead. All right, so unfortunately, based on what I was seeing, I think that'll only fix it if we eat a ghost and we are above kind of the midsection, because there appears to be that one little spot that they get stuck. And so maybe what we need to do is when we're going in the upward direction with Clyde, so let's see. An option would be to create a brand new movement algorithm for when they're dead so that they always take the fastest route back. That might be the best way and most professional way to do this. Let's see if we can fudge it just a little bit faster than that. So let's start by saying if we're going up and we can't turn upwards, then maybe what we should do, and then if our target is off to our left, then what we should do is, okay, elif. Now we should probably just check and see elif And then for some reason, the first default thing it's doing, because it can't do anything logical, is going back down, which is this 3. So now we'll just say, actually, let's make the default movement to the left. So let's put 1 before 3. And now when it's stuck in that little awkward, bizarre chunk that it was in before, now it should go left by default. So I don't know if that'll fix it or not. I guess we'll find out together. But let's go over here. Let's grab a power up. And let's eat some ghosts. 1, 2. All right. Please, guys, go back to the box. And they go left. All right. Nice. So now please go in the box. And bam, they come back alive. Okay, that's awesome. I'm actually super thrilled with that. You can see they kind of clump up right now unless we have them scattering because of the power up. And that's because we've given them all the same movement algorithm. But let's go ahead and see. Oh, that's interesting. He is in the box a little too early. But then I collide with one and it resets. So that's cool. It looks like the dying collision is working pretty good. Let's go ahead and grab another power up, eat another few just to test if in these various different locations. Oh, I forgot. I made them pretty fast. So actually, I think this is a good chance to do to make, rather than ghost speed, let's make ghost speeds. Okay, so let's come up to where we had ghost speed initially. And let's just make a list for the 4 of them that's going to have all their speeds listed out separately. And then we'll come down where we gave them speed and we defined the classes. So in our main while loop, while run, where we define them, instead of ghost speed, let's make them ghost speeds. And then it'll be 0, 1, 2, and 3. And this way we can control all of their speed individually. So if they're dead, they're supposed to be super fast eyeballs that can get back really quickly and directly. And then if they're just alive and cruising around, they have a speed of 2, I believe. And then if they are eaten, then the speed is going to, or if the power up is active and they're not eaten, then it needs to be a speed of 1. So we're going to kind of slow them down. So let's just come up here where we define the center X and center Y and add some checks. So if power up, let's say by default, all the ghost speeds are going to be equal to 1, 1, 1, 1, because they should all be slow. And then we'll add a check in here, which is if Blinky dead, then we want ghost speeds 0 to be up to 4. And we're going to use this same little check for all of them. So we're going to let those eyeballs speed back to the box. So let's see. Blinky dead, Inky dead, Pinky dead, and Clyde dead. You're probably getting pretty sick of those. All right, so 0, 1, and 2. Oop, how did that happen? Okay, 0, 1, 2, and 3. All right, and that's great. That handles everything if there's a power-up active. Now let's kind of check out the else. So we're going to have an else. Ghost speeds is going to be equal to 2, 2, 2, and 2. And then all this, if Blinky dead, if ghost speeds, all that is going to be the same. So actually probably the best way to do this, right? You guys are probably there already, is to do it this way. So if, and then else, and then modify all of these. So basically this is saying, all right, if there's a power up active, then all the speeds should be 1. Otherwise, the speeds should be 2, which is normal. But then if any individual ghosts are dead, we're going to give them an extra speed boost so their eyeballs can get back a little quicker. Alrighty. And let's take a look and see if that solves anything. Alrighty. So they get out. Okay, which is good. Let's see. They slow down when I eat the power up, which is awesome. And then those eyeballs get to go really fast. But you can see Pinky now, that's happened twice. Pinky's managed to be alive a little too quickly, hasn't really gotten back in the box. So I think we need to take a look at our self.inbox checking and just update the Y a little bit. So I believe we did check for self.inbox inside of the ghost when we are, in check collisions here. So what we'll do is the Y, rather than 490, let's make it a little bit higher up. So 490, we want to come up a little bit more, 480. So now they shouldn't be able to bump into the bottom of the box. and then immediately come back to life. So let's see. I don't know how easy that's going to be to test it. Waka, waka, waka. There we go. All right. So yeah, that time I think it was very similar to the previous time when I ate those ghosts. It was pretty cool. So also, I don't know if you saw there, but it looked like the ghosts were not smart enough to get out of that box while the power-up was still active. So I think what we need to come down here, if not Blinky dead, if power-up, then this is making them want to run away. So if not Blinky dead, then this is making them think that they're currently like the spooked ghost. So we need to have this, if not Blinky dead, and not eaten ghost 0. And now we need a third rung in here. So we need an if and then an else if and then an else. And so we'll do else if not Blinky dead and we have already eaten this ghost. So that means you've gotten back in the box, and then we want the regular target of the player. So this should help him get out. Actually, this means you're going to be in the box. So we need to add 3 tiers, right? So we need this, hey, let me get out of the box, and then this guy. So we need to basically copy these exact conditions now. So, but we need to tweak it slightly. So let's go like this, shift. And then we'll say if, and then we'll come down here and we'll make 2 new conditions for this guy. All right, so if not Blinky dead, we have a power up active. So Blinky dot dead, and we have eaten this ghost already. That means you've made it back to the box at some point. Now we need to check and see, okay, if I'm in the box, let me get out of the box just like normal. Otherwise, I'm targeting the player, and we just have to add essentially this exact bit of code to all of them, okay? So if not Inky dead and not eaten ghost, what 1 now, right? Okay, so if not Inky dead and we have eaten the ghost, then that means if we're back in the box, just get out of there. And then once we're out of the box, we want to target the player, okay? So I hope this makes sense, you guys. It is hard doing something like Pac-Man where you have 4 enemies that all have to kind of operate individually, although with some shared rules, but then they all kind of need their own personalities, and we have to catch all these various scenarios. It gets pretty complicated, but if you thought that one of the most popular video games of all time was not going to be a little bit complicated, I'm not sure what you were hoping for, but I've tried to break it down in the simplest fashion I can, and I hope we're getting there together okay. All right. So we just got to make sure we get our variable names right, and then if not Clyde dead and not eaten ghost 3. Okay. So this is obviously a lot of work for a pretty niche scenario, because you could always just wait for the power up to kind of wear off, and then you would still end up getting the ghosts leaving the boxes. But let's see if that handles that. All right. So they get out of the box first time, which is pretty good. And now let's get a power up and let's eat these guys. All right. And let's see if I can go get another power up, because that should give us time to see. Yeah. So they get out, which is great. And then now they're ghosts again. And I guess this is an interesting scenario because we have 1 ghost trapped in the cage. I'm not actually worried about that. I think that's pretty good right now. So let's see. All right, well, they all go there and then they all get out pretty well, which to me, this is working pretty good. I guess we have to give you some score, I think, when you eat the ghosts. I believe it's 200 times however many ghosts you've eaten. So I think the way the scoring works is if you eat the first ghost, it's 200 points, and then 400, and then 800, and then 1600 if you manage to eat all of the ghosts. So we already have this pretty easy checking for collision. Where was that? Yeah, okay. So all we need to do is check the ones where if it's power up and we haven't eaten the ghost yet. So we're going to check in the 4 where we actually get to eat the ghosts, which should be these bottom 4. Yeah. we're going to just say score plus equals and then 200 times and then a count of how many times true is in the eaten ghosts list. So eaten ghost true. And actually, this is, you got to get the format right. So eaten ghost dot count, and then you give it the value to count. So the number of trues that are in here. So this is going to work because we're putting it after we write this one equal to true, or it should work, I guess. So let's see if we can get a scenario, and this exact one is going to work for all 4 of them. So basically, it should be 200, and then 400, and then 800, and then 1600. It's maybe going to be a little tricky to test live, and that's something we threw in pretty quick, so there's a chance we got that function wrong. Let's just take a look here. So I'm sitting at right around 170. I should be able to get 2 or 3 here. I got 2. Yeah, and the score jumped a lot. I'm not exactly sure if it jumped. Oh, yeah, because I did get 3. So I got 200, 400, 800. So I should have gotten about 1200 there, and I think that's exactly what I got. Let's see if I'm able to eat just like 1 or 2 ghosts at a time. Probably not, because they're kind of clumped up because they still have 1 movement algorithm, but I'll get 2 here. 18, 30. I got 2 of them, and I went to 2530. So that's, what, 600 extra? I got another one, and it went up by, what was that? Oh, okay, so it's not 200 times the number of ghosts I've eaten. It's power math. It's exponential, because 200 and then 400. Yeah, okay, so it's 2 raised to whatever power. So 2 raised to the power of the count times 100. I think that should do it. So if I've only got 1, then this will be 2 raised to the first power, which is 2 times 100. But then if I've eaten 2, this will be 2 to the second power, which is 4 times 100. Okay. Great math, everybody. So essentially, we can't just say 200 to whatever power, because 200 squared is like 40,000 or 4,000. You do the math. But it's 2 raised to whatever power of the number of ghosts we've eaten. So if we've eaten all 4 ghosts, it's 2 to the 4th, which is 2, 4, 8, 16, and then times 100. So this is really the correct way to do scoring, which is great. And now let's take a look at our checklist. So we have lose a life, and then eat ghost, and send running back to cage if power up. So now what we want to do is we're going to take our move Clyde conditions, and we're going to give all the ghosts their distinct movement personalities. So instead of all of them moving like Clyde all the time, we're going to move Blinky, move Inky, and move Pinky in all their unique ways. All right, and so the thing is, Clyde, we know it's a good movement kind of algorithm for getting in and out of the box and everything. And so we might give the rest of these ghosts some movement commands that are a little bit non-logical if you were dead. Like, they won't necessarily always take the most direct turn. And so what I think we'll do is we'll come into this if moving, and we're just going to update the ghost commands a little bit. So we're going to still have them all use this like move Clyde if they are dead. So what we'll say is, if not Blinky dead, and not Blinky in box. So basically, if we're in a scenario where we're just roaming around the board, then we want to have all of this that we currently are doing with move Clyde with a new function that we're going to call move Blinky. Okay, but then we'll say else, so else on this guy. Then we want to keep it exactly how it is today. So we want to still move Clyde because it's not actually moving Clyde the ghost. It's the algorithm we wrote specifically for moving Clyde, but we know how direct it is. So we'll say if not Pinky dead and Pinky, then we're going to have all of this jazz come from Pinky, move Pinky, and then we're going to have Pinky else move Clyde just like that. Okay, and now we just do it again for Inky, and we actually don't have to do anything for Clyde. We are going to let Clyde just move like Clyde all the time. But I think maybe this will become a little clearer why we're doing this. Inky.move Inky, Pinky.move Clyde, Inky.move Clyde. So let me make sure everything says Inky here. Everything says, oh, yep, there we go, Pinky direction. And then this needs to be Pinky.move Pinky. Okay. Yeah, silly names. And we'll just leave Clyde alone because that should be totally fine. And this is all, of course, underneath if moving. So only if we've started up in the beginning are these players going to move. And then if we reset and everyone goes back to their beginning spots, then they won't be moving again for 3 seconds. So this is very cool. This should work. We just have to make move Blinky, move Pinky, and move Inky. And I guess the thing is, I'm going to put all of these in the class, and you may say that doesn't make a ton of sense because it's specific to each ghost, and that's fine. But I want all the ghosts to be able to use the Clyde algorithm at times. So like if you wanted, you could make it to where depending on the level they're on, they all behave in a different one of these algorithms that we create. So even though we're naming them after the ghosts, it doesn't work that way. We're giving them all 4 functions that they could access to move in different patterns. So that's why I'm putting it inside the class. It would be totally valid to put this outside and make it kind of separate as well. And so now let's say Blinky is going to turn whenever colliding with walls, and then otherwise continue straight. So essentially, every time Blinky makes a turn, Blinky's going to continue exploring in that direction unless they collide with a wall. So that'll be kind of our generic theory of movement behind Blinky. And so let's just start going through the directions. And we're going to go a little faster because we already have most of the scenarios caught in our algorithm here. So it's obviously going to stay the same for if I'm going to the right and I'm able to keep going to the right and my target is over there, then keep going. But then if not, so this means I've collided with something to my right. And then we're going to still say if the target is above me, then turn up. And then if the target is below me, then turn down. And so we don't have to change those. And then if the target is to my left, turn left. So that's nice. We can keep all of that there. And then we'll say, let's just pick an order. So 3, 2, 1 really seems fine to me. I don't think we have to mess with anything just yet here. And then if self dot turns 0. So now rather than checking if we can turn up and down at all times like Clyde does, we're going to say, you know what? If I am able to keep going right, I'm going to keep going right. So basically the way to read through these scenarios is if I can't turn right anymore while I'm going right, then I'm going to make all of the same turn decisions that Clyde does. But if I'm going right and I'm able to keep going right, then I'm going to. So basically that is Blinky's whole movement thing. And you could say like, well, Blinky on its own would probably never catch the player because it would be really easy to juke him out. And that's true, but actually with the 4 ghost algorithms, what we're really trying to do is get them all moving in slightly different ways that are still generally towards the player. And so you're kind of creating a trap, like a box. And you'll see it actually works really well. It becomes pretty challenging. So yeah, bear with me and let's keep going. So basically, if self.turn. So now we're at self.direction equals 1. And we'll keep this if my... and actually we'll change this first one to... So we'll get rid of this from Clyde, and we'll just make this an if instead of an elif. So basically, if the X target is behind me and I'm going left, then just keep going left. Otherwise, if I've collided with something on my left, then okay, check if I can go down, and if I can, I will. Check if I can go up, and if I can, I will. Check if I can go right. And all these first 3 are target specific. So they're seeing, like, can I make a logical move that will allow me to pursue my target? But if I can't, then we'll do 3, 2, 0 now instead of 3, 2, 1. And then all we have to do, again, is update the, okay, I'm going to just keep going left if I can kind of code. So this, you can see this is taking way less time than creating Clyde initially because we sort of built the framework out already, and now we just get the benefit of sort of tweaking it so each ghost has its own personality. All right, so before getting too far ahead of ourselves, let's go ahead and get in 2 before we break an elbow patting ourselves on the back. So now If the Y target is above me and I'm still able to keep going up, then obviously I want to keep going up. I guess this self.direction2 can stay there. It doesn't need to be there because the direction's already 2, but it doesn't hurt anything. All right, so then if I can't go up anymore, I've collided and up, and now we'll check to see if we can go to the right, and if we can, we will, to pursue the target. Same with the left, and then same with down. And now we can pick a direction of movement kind of command, and I think for this one, instead of 130 like Clyde had, we'll go to 301. And again, this is just where the ghosts get their little prioritization personality. So now we're just saying if I've collided with something going up, rather than going left or right first, I'm going to go back down first, just kind of as a default. If you don't like the way he moves, then you can just change it yourself. That's totally fine. But then we'll say, okay, otherwise, if I'm able to keep going up, keep going up. All right, so that should make sense. And most of the time, you're not even going to notice these three, I should say, because most of the time, making a turn when you collide will make sense for your game. Like, it'll make sense to go left or right when you've completed a turn. Okay, so now we're at direction 3. We're almost done with Blinky, which feels awesome. So if direction 3 and then self.target 1 is greater than Y pause and turns, then keep going downward. Yes, that's great. And then if not self turns, 0 gets to stay the same. 1 gets to stay the same. And then, yeah, 2 gets to stay the same. Okay, so that's really great. And then 2, I think maybe we'll just do 201 instead of 210 again, just to change him enough from Clyde that these ghosts should not typically be directly overlapping one another for too long. Because they should make different decisions at a variety of turns while still generally heading towards the player. All right, it's very difficult to create ghost movement that looks intelligent and different from one another, but still interesting and logically pursuing the player. So hopefully this all makes sense, and hopefully you think it's pretty fun, but don't give me too hard of a time if it doesn't make sense to you, okay? All right, so I think that's great for move Blinky, and I think what we'll do is we'll actually move Clyde for all of them. We'll copy move Clyde as the framework for all of them because we know how thorough that is. So rather than try to tweak move Blinky for move Inky and then rather trying to tweak move Inky for move Pinky, we'll start all of them from a move Clyde basis because we know that was a really thorough catching all scenarios kind of algorithm that we built. So now I think what we'll do for move Inky is we'll say that Inky turns up or down at any point to pursue, but left and right only on collision. So this is kind of halfway between what we did for Blinky and what we did for Clyde. So Clyde, essentially, if at any point he can make a turn that will pursue his target, he's going to make it. Blinky is only going to make turns to pursue the target on collisions with walls. Inky's going to do half and half, turn up or down at any point, left and right only on collision. So let's just start at the very beginning and take a look at what we need to do to make that a reality. All right, so let's just kind of go from the move Clyde framework, and we'll still say if we're going right and the target's over there, then it still makes sense to keep going. And then we'll say, okay, otherwise if I've collided, and we shouldn't have to change too much here, I'll still go direction 3, 2, 1. When I collide with something in the direction that I'm going, I'll check if those are logical. I'll leave 3, 2, 1 in place as well. And then I'll say if self.turns 0, and then I will still check if it makes sense. So actually we're going to leave direction 0 the exact same as it was for Clyde. And I think direction 1 is going to be the same, right? Because we're going to keep going left and right. We're going to keep going left and right just like we would with Clyde. So the immediate turn up and down if it makes sense. So now let's go ahead and check out what to do with if self.direction, if self not turns. And now let's check out what to do with self.direction 2. Okay, so if we are going upward and it makes sense to keep going upward because our target is up there, then we're going to keep doing that. So that is going to be getting rid of this initial if. Now elif self.turns, and we can't turn to, then we want to say if self.target 0 is greater than x. We want to go right, yes, left, yes, and then down, yes, and then a 1, 3, 0 for this is totally fine. Elif self.turns 2. And here's where we're going to say, okay, rather than checking if it makes sense to turn when we collide, if we're able to keep going down, which is what if we said for left and right, if I'm able to keep going left and I'm able to keep going right, but it makes sense to turn to pursue my target, I'm going to do it before continuing in my same direction. So that's what we're keeping in place for X and Y, or for left and right. But for up and down, we're changing this so that you'll keep going up or down as long as you're able to. So that's what we meant when we said Inky will turn up or down at any point to chase their target, but left and right only on collision. So only when I finish going down or I finish going up are we going to have Inky turn. All right, so we just need to come through and make the exact same change now for 3 down here and basically get rid of these ifs and elses. And so you can see from the Clyde framework, who is pursuing all of the time, we can create these 4 distinct personalities without rewriting all of the code every time, which is huge because this would be like a 14-hour video if we had to do that. Okay, so now hopefully this makes sense to you guys. All we're going to do for Pinky, who is going to be almost the opposite of Inky. So Inky is going to, I got to change the name. Pinky, there we go. Pinky is going to turn left or right whenever advantageous. So it works for him, but only up or down on collision. So this way we've taken, the Clyde will turn at any point, Blinky will only turn on collision, and then Inky and Pinky will turn at various times that make them different from the other two, but we've created these 4 different movement patterns that are still predicated on ultimately pursuing the player. So it's pretty cool, and I actually think this is some really, really cool code that we've whipped up here. But for Pinky, we just got to come down into our self.direction checking, and we need to say if I'm able to keep going right, then I will. So we will just come down and say elif self.turns 0. And then what I want to do now is just say if not inbox or not self.turns. No, you know what? Let's just, for now, let's just do it like this, and let's see if that's all we have to do, because I think it should be. We leave our up and down as is, and then we tweak these just like we did for up and down. All right, and then let's check and see if this gives them any trouble getting out of the box or not. It shouldn't, because they all move like Clyde when they're in the box. But okay, if you have questions about what we just did or how it's going to work, let me know. But hopefully when I boot this up now, we're going to have 4 different movement patterns. They're all going to kind of get out of the box the same way they already did. And then we should start seeing them kind of scrambling and making different decisions. And so far, they're really still clumped up. And okay, well, there you see Clyde and Pinky move a little bit differently, although not super logically per se. So let's see. They're going to pursue in the same fashion. Red's coming after me. Damn. I'm trying to test their pursuit angles, and I can't even stay away from them long enough to survive. Okay, so let's see. It looks to me like, yeah, there you go. Clyde was the only one who turned immediately to come chase me, and he got me. Damn. So this is where I was saying the game actually gets pretty hard. Let's see if we can eat some of them. That should get them to scatter a little bit more. So, bam, got you. And then got you. Nice. Oh, that's interesting. The Inky there, it looks like managed to not even have to go. Dang, I didn't get the power up. Didn't even have to go in the box to reset. So we maybe have a few more bugs here. Eyeballs. Okay, well, they had to go in the box. That looked pretty good. So let's get away from the ghosts a little bit. Oh, red's going to get me. There we go. Oh no, red's not going to get me because I know the movement algorithm. All right, so yeah, you can see they're spreading out a little bit, which looks really good. Let's see if I can go get them. So 3010, this should give me 200. It did. Let me see if I can get a second one. It did. Yeah, it gave me 400. All right, so the scoring updating is working too. They go back in the box, which I think is really awesome. And then they're just trying to make these different decisions. And actually, you can see here they've got me boxed in pretty good. Yeah, I'm going to die. Although the collision didn't. Oh, because I'm out of lives. So they killed me, and we haven't handled how to lose yet, which is great. But you can see the various ghosts all pursue in their own ways, and it sort of creates this like entrapment, which is really cool. That's the whole point, is these ghosts should have their own personalities, and as you cruise around the board, they're kind of slowly creating this box that at times will make it impossible to escape. So like there, I was literally trapped. But it's great. They slow down when we eat the power up, and they turn into eyeballs, and they run back to the box when they're dead. And then as soon as they're not dead, they manage to get out, and they manage to be alive again. I did notice that even after they come back to life, they're still slow because the power up is active. So I think what we need to do is in ghost speeds. Where's ghost speeds? Down in the main while loop, right? So in our ghost speeds logic, we need to figure out if ghost speeds. So we need to add some here, I guess, which is just if eaten ghost 0 and Blinky dead. So actually, we'll do these. Yeah, okay, this is good. We'll do it above the dead checks. So that way it'll kind of be like the stuff gets overwritten based on what's more important. So eaten ghost, eaten ghost, eaten ghost. It's like Eaton Park. Ghost, ghost, ghost. And we'll take these 4 lines of code and we'll put them before the dead check. Okay, so basically, if I have eaten a ghost already, then the speed should go back to 2 once the ghost is not dead. But if the ghost is dead, speed should be 4. So it's kind of like the order here really matters. Basically, if there's a power-up, all the ghosts should be slow. Otherwise, they should all get speed 2. But if at any point there's been an eaten ghost, even if power-up is true, then the speed goes back to 2 once they become alive again. But then if a ghost is dead, it should always get speed 4 because now it's just eyeballs and it has to get away. So that's kind of one thing we should add there to fix that little bug. But I'm at this point where I'm super happy with the movement algorithm. So I think what we should do first is handle game over, and then we will add in sound effects and some restart and winning. So let's take a look at what we should do when the game is over due to dying or winning. So it's going to be kind of similar. We just have to check for 2 different things. Dying, we're obviously checking to see if we are out of lives. And winning, we're checking to see if there are no pieces left that we need to eat on the board. So they're both going to result in essentially a pop-up window that's going to tell you like, oh, game over, press spacebar to restart or enter to restart or whatever like that. But we have to check 2 different things to trigger it. All right, so the first one is going to be going back up to all the places where we could lose a life. And so that would be in here. If lives is greater than 0, then we do all this other stuff. Let's just add an else condition to that, because that means, okay, well, now I don't have enough lives. So we'll say else, and then game over, which will be a new variable we make, equals true, and then moving equals false, and then startup counter equals 0. And then the only thing is we're going to have to make it so where game over makes it to where the moving counter doesn't go. Okay, so we got to come down in all the places where we lose a life. So that's, I think, all 5 of these, yeah. Minimize the if there, and we'll just throw an else in. Okay, and then in here, we'll minimize the if, throw an else. And they're all exactly the same, which is nice. If, and then else, and then shift tab this bad boy back a little. There we go. And then I think we need one more. There we go. And so essentially, these are all the times you could lose a life, which would be all the times you could make game over. All right, so let's go ahead up to the top and define a new variable we'll call game over. and we'll set it equal to false in the beginning, obviously, but then we'll also say game 1, which also equals false, but we're going to want to use that for the other kind of check. So in either case, we want the movement to stop, and so basically we'll come down in here and we'll say if startup counter less than 180 and not game over and not game 1, right? Because we don't want to keep everyone moving. So actually moving is false. Whoops. Or so we want, this is the situation where we're not moving. Else moving equals true. Oh yeah, no, that's okay. This is good. So this is saying moving, which is already going to be equal to false when game over or game 1. So moving will stay false. We just won't update the startup counter if game over or game 1 is true. So that should work. All right, now we need to come down into just kind of our draw function, and I guess we'll go into draw miscellaneous because we have this nice spot where we can put stuff already. And let's just say if game over, then we'll pygame.draw.rect, and we'll put it on the screen. And first let's make a white rectangle to kind of be the outline. And let's have it start at, I don't know, 50 for X and then 200 for Y. And let's have it be 800 wide and maybe 300 tall. And let's just make it solid. So that's a 0 for thickness if you want to make it a rounded rectangle, which I do, with radius 10. And then I'm going to draw a black rectangle inside of that. So pygame.draw screen, and then a black rectangle, or I guess we'll make this dark gray just for some separation. And we'll put it like a 20 pixel inside of the big rectangle. And so this is going to give us a nice little, so this needs to be 760. And then this should be 260. And this is just going to give us a nice two-tiered effect for our like menu. We're gonna put text on here. So we'll make a new font, but for now I'm just gonna show how to do it. Let's do it this way: game over text equals font.render, and we're gonna put some text on the screen that says like game over. So game over space bar to restart. Okay, and we'll just put this on the rectangle that we're just defining right there. So screen.blit, game over text, and then position-wise, we've got sort of 50, 200. We've got a pretty good square there to put it on. So we'll make this bigger text eventually, but for now I'm just going to put it on like 100, 300, just as a kind of to get a feel for what that looks like. And then let's take kind of this exact same thing and just say if game 1, we'll draw the same menu rectangles, but now it'll be game over text is going to be victory, spacebar to restart. And so obviously we're not actually doing anything super different with the 2 right now, but it's just because we haven't put in like score saving or high score tracking or anything like that. But then what we want to do is we want to come down into our event handling, and in key down, we just want to put if event.key is equal to pygame.k underscore space, so like that. And now we want to check and see if game over or game 1. And in either case, if we do that, then we want to take all of the stuff we do when we reset these guys, and we just need a few additional things in there as well. So this is kind of our built-in restart stuff already. And what we're going to add on top of this is score equals 0, and we're going to give lives back equal to 3. And that should be all we have to do to get to restart, but I'm sure we'll see if there's any mistakes. I think actually what we want to do here as well is we want to reinitialize the board. So we need to take level and set it back to its initial value. So let's take a look and see where level is. Level equals boards. Yep. And you just want to, when you restart, you want to reset your level to what it started at. And then we need to make game over and game one both false once we go back to start. So game over equals false, and game one is equal to false. And so now the space bar, once we've lost or we've won, should really give us an opportunity to restart the game. So let's take a look if that works. And I guess first I'll just try to lose. So we'll test that first. So I lost a life there, which is great. Thrilled to have lost a life. Lost a second one, and let's go lose a third life. And I think I get one more life, right? Yeah. Okay, so now I need to die because now I'm at 0 lives. And so this should... Oh, function takes at least 3 arguments, and I only gave 1. Oh, yeah. Because you for font.render, you can't just give it the text as much as I would like to. So let's go back to draw miscellaneous. And this text that I did, game over to restart, you also have to give it the anti-alias, and then you have to tell it what color to draw the text as. And I guess let's just do it to be a little fun. Let's say game over text is going to be red, but game one text will be green. All right, so because this takes a little while to test, I'm going to dip lives down to 1. Just so I only have to die twice to test this. And I'm going to kind of go die twice real quick. All right, so now this should give me something new. Bam. All right, so the ghosts are still moving. Game over, spacebar to restart. Let's see if I press spacebar if the game actually resets. Yeah, so I get 3 lives. Score goes back to 0. The board did not come all the way back. So I think we might have to re-import it. Let me see if we do it this way. Because we are overwriting the level every time we eat something. So we're actually changing what board is equal to. So level equals boards. And let's say level initial also equals boards. Let's see if we can set level equal to level initial, because we haven't changed that the whole time. All right, so level equals level initial. And I don't know if that'll work, but it should. All right. Just got to die twice. I could have made live 0. Yeah, that would have made testing even faster, but you're 4 hours into the video. You really care about 30 seconds? Game over, spacebar to restart, spacebar. No, so those dots don't come back. That is interesting. So let's take a look at maybe how to fix that. Level equals level initial. I bet because we're not overwriting it in the board's file, maybe we just need to do the import again. Import boards, and then level equals level initial, and level initial equals boards. You'd think this would store it the whole time. I bet so many of you guys know what's going on here. So when the player checks for collision, if the player collides, then we change the value of the level at that to 0. But that's so interesting because it's just a list of integers, which is equal to boards. And so we should be able to overwrite it. Let me see. Maybe we can directly just pull it from level equals board dot boards like that. Maybe that'll do. Unresolved reference import board. I already did. Oh, things are getting goofy now. Let's see. All right. And let's die one more time. And come on, reset the board for me when I press space, and it does not. All right. Okay. All right. We're going to figure that one out. So let's set this back to what we had initially, which is just level equals boards. And I'm going to get rid of that extra import statement, and we are going to, so we don't need this. And we are going to let's see, get rid of that initial board, just kind of put things back to how it was before this, although there's so many variables I'm getting turned around. And let's take a look at how to fix this. Okay, so what's going on, and this has happened to me a few times, is we're modifying the base list while we are actually overwriting. So when we eat pieces, it is changing boards like the list. The only thing is we never save our changes, so this list always looks the same once we're done running the game, but momentarily we're modifying the root list that we're copying this from. So the actual way around this is, rather than make this just equal to boards, is we're going to do something called a deep copy, which means copy the entire list but leave the original intact. Basically, that's the easiest way to think about it. And so this is another thing that we need to import. So we need to add that import up to the top. But now what's nice is when we modify the level throughout this level, once we have the reset, so once we have the reset down here, where we try to set level equal to boards, well, we're just going to say when it's time to reset, we're going to do another deep copy of boards, so that level will always be an original. So now if I boot this up and I go get eaten real quick, if I restart, we're going to get the pieces back because we're no longer modifying the original when we play this game. So now we're modifying a copy of the original list, which makes it way easier to reset. Okay? So fun little deep copy introduction there for you if you haven't seen that before. If you have, then sorry, it was fun and exciting for me. Okay, but so now that kind of will handle what to do if game over and we lose, but we haven't ever set game 1 equal to true yet. So let's come down just into here, and this is actually a pretty easy checker. Okay, so we're just going to come kind of in here. It's a fine place to do it, and we'll say for I in range length of level, and then for j in range length of level, and then we'll say if let's see, if 0, actually we don't even need this second one because level I is going to give us a list that'll be really easy for us to check for. So we'll basically start every single iteration by saying game 1 is equal to true, but before we can do anything with it in the code or use it anywhere, we're going to set it equal to false if there's a 1 or a 2 in the list. So we'll say if 1 in level.I or 2 in level I. So this is basically saying if there's a 1 or a 2 in the row, then game 1 is equal to false. Okay, so this is just a really quick and easy for loop that's going to cycle through the entire list and see reasons to turn game 1 off, to turn it to false. But most of the time, this is going to really quickly turn it equal to false. And so we can just kind of leave it this way, because by default it'll say game 1 equals true, but we're not going to do anything with it until we find that there's no 1s or 2s. So really quickly, let's see if we can get this win, if we can get this dub. All right, so let's go ahead and eat a ghost. Cool. Let's turn left. Let's go down. Let's go to the left. And I've got 3 lives, and I've played Pac-Man a little bit before, and I wrote all the movement algorithms for these ghosts. So hopefully I can get this win. I can semi-predict how they're going to move. Oh my goodness, I'm so stupid. Okay, all right, well, that was a good start. There's evidence that the ghosts are eventually going to box us in. All right, let's get this guy dead. And let's go over here. Try to clear this corner out, I suppose. I've got 2 lives, which is nice, but I'm a little worried about going into corners like this. Okay, I can get away from these guys. And it helps that none of them are actually faster than Pac-Man. I think in the original game, their speeds might be a little more varied. There might actually be a ghost who is slightly faster than Pac-Man. You're welcome to mess with those speeds and times as much as you want on your own. I have honestly I'm super thrilled with how this came out and how this is looking. It's looking really cool. Oh, crap. Okay, so I got 2 more chances, and I only have 1 corner of the board, really, so I think I can probably do this. Let's see. I'm going to slide through the side here. Clyde's going to chased me. Nope, turned around. Right, because we told him to turn anytime it was advantageous for him. Okay, all right, gotta get away, gotta get I actually think I navigated that fairly well, all things considered. Okay, let's see if I can get some more points before I grab that last power up. And let's just, bam, eat Pinky. I love their little ghost eyes running away. It's super fun. Okay. And let's clean it up, clean it up, clean it up. There we go. Victory, spacebar to restart. Okay, so honestly, guys, I think that what we've built here is the absolute essence of Pac-Man. It's obviously a doozy of a project. I think it is the biggest project that I've ever made on the channel by far. Over 1,200 lines of code, not counting the board, which is an extra 40. And so this is just really massive. We did all kinds of things. We did classes, we did functions, we did parameters. There was animated, there was pulling in images and JPEGs. You know, I think that probably the remaining things that could take this over the top would be adding sound, adding more levels, adding maybe a menu in the beginning, or high score tracking. These are all concepts that I've covered in past videos on the channel, and I think they could really help you take it that extra mile on your project. If you have any specific questions on how to add any additional functionality to this project, feel free to let me know in the comments below. I'll kind of talk you through that process. I'm not going to spend too long doing things that I've already shown how to do multiple times on the channel, especially because this video is so long. It's taken a ton out of me and I'm just super drained. But we've got these 4 ghosts acting in all their own unique patterns. We can eat them and send them running back to the cages. We can get power-ups. We have score tracking. So I just think that this is an amazing project we've built together. I hope you guys have found it useful. I'm a pretty small channel still, obviously, and so if you would consider telling a friend who might be interested about the channel, that would be amazingly useful to me. If you're not subscribed already, be sure to subscribe to the channel just to stay up to speed on all the cool new projects like this. We will be advancing into some basic robotics and electronics concepts in the coming weeks as well. I have an Arduino kit that I'm going to start doing some basic home automation projects on the channel with. So that kind of stuff is super exciting. Be sure to subscribe to the channel. Make sure to stay up to speed on all those projects. And thank you so much if you stuck it out, watched this whole video. I really appreciate you guys being here and subscribing to the channel and watching these videos. It's why I do it is just so that you guys can all get this cool experience, and hopefully we can all learn to be better programmers together. So with that being said, thank you guys so much from Lemaster Tech. Until next time, good luck with your code, and thanks for watching. Thanks. Bye.